Okay, so it's my great pleasure then to continue our scientific program. Let me just make the presentation for you. It's my great pleasure then to give to all the attendees the welcome to the day 4 of this conference. It's my great pleasure then to present our first speaker today, Professor Igor Reznichenko from the Keldysh Institute of Applied Mathematics in Russia, who will talk about on-quadrature formulas for a simple larger potential. So, Professor Reznichenko, thank you very much, and please continue.
Okay. Pleasure to be here. Hello, everyone. Thank you for a professor yet, just a doctor. And it holds through. If you cannot hear me or see the slides, please feel free to stop me. And I will be talking today about a certain way of solving the Laplace equation, specifically in the three-dimensional case. Using special functions called layer potentials, one can construct solutions to boundary value problems for the Laplace equation and reduce them to Fredholm integral equations of the second kind. A large number of problems in mathematical physics are reduced to boundary value problems for Laplace equation. Let's start by introducing a Cartesian coordinate system in a three-dimensional space. I will be mentioning the surface gamma a lot in today's talk. Let's assume that gas C2, I'll speak more in detail in a minute, and this surface gamma bounds a volume single connected interior domain D, for which we shall consider an external Newman boundary value problem for the Laplace equation with the boundary condition defined on the surface gamma. Now, I will be also mentioning the normal derivatives a lot. So the normal derivative is set on the surface gamma, and we will be talking about it. That the normal derivative is, in a way, the key to the method I'm going to describe soon. Now, the problem 1 is uniquely solvable and we're going to find the solution in the form of a so-called simple layer. Now, it's a surface gamma, and it represents the potential density for the solution consists of two stages. First stage involves solving the boundary integral equation, the Fredholm equation of the second kind, which in our assumptions is known to be uniquely solvable. This is one of the main advantages of the boundary value problem, or the boundary or the potential method, is the fact that the dimension of the boundary integral equation with respect to the unknown values of the potential density is 1 unit less than the dimension of the original boundary value problem. This greatly helps in some situations where you need that additional computational speed for your specific task. Now, once you have found the values of the potential density on the surface gamma, you can simply substitute these values for the expression 4, which is the solution. So, as I've said, we are searching for the solution in a way of a simple layer potential, which can be proven is the solution of the external Newman boundary value problem. A quick overview of the problem at hand. The integrals in the simple layer potential and also in its normal derivative are generally hard to find explicitly. At the same time, while you do need to use special numerical formulas to find these integrals, so-called standard quadrature formulas for the simple layer potential, which are used a lot in applied calculations, do not provide uniform approximation and uniform convergence near the surface gamma on which the density is specified. So as the distance towards the surface decreases, these formulas tend to go to infinity with a fixed step. This creates a desire to develop some alternative methods of numerically obtaining the values of this function. And the work I'm going to be talking about today is based upon a paper my co-authors published in 2019. It was the first attempt to tackle this problem at close ranges to the surface for the simple layer potential, the harmonic simple layer potential, meaning that it is the solution of a Laplace equation. Now, in this work, the goal was to first obtain a new quadrature formula for the potential itself, preserve the property of continuity, at the same time, the quadrature formula for the direct value, that means on the surface, of the normal derivative of the potential. So this would accommodate the first step of the solution, the acquisition of the potential density mu. So Newman boundary value problem for the Laplace equation. I will mention very briefly some notable mentions in literature in solving similar problems. For example, the first book you can see here, published in 2002, introduced a peculiar method for infinitely smooth curves. The idea was to solve integral equations based on the Fourier transform. However, these methods were mainly applicable to the 2D surfaces, basically to a plane, not the 3D case. Mentions is the paper published in 2013. It's usually called the QBX method, and the short description of the main idea is an auxiliary point is chosen near the surface, then a special coordinate system introduced at that point, near which the potential kernel is expanded into a series of Legendre polynomials. This method has its advantages. However, the use of local coordinates is not always advantageous from the point of view of the time that will be spent on solving the original problem. Now, here is here are the contents of the work. First, I will be talking about the quadrature formula for the potential itself, then its normal derivative, and when we're going to apply the two of them to the solution of a boundary value problem. Now here I'll make a quick stop and ask if everyone can hear me correctly. Does anyone hear me? I hope you can. Well, I'm going to wait a little bit here because I'm not sure if everyone hears me. Professor Sanchez, do you hear me? Well, I'm going to wait for half a minute and then I'm going to continue. Hello?
Yes. It's okay.
Can you hear me well?
Yes, it's okay. For me...
I was just sure that the connection is stable. So, okay, I'll continue then. Thank you very much.
Welcome.
So, the contents of the work are as I've described. So, let's go forward with the first section. Let me define the surfaces under consideration and their parameterization. We introduce a Cartesian coordinate system in space, in a three-dimensional space. Let gamma be a simple, smooth, closed surface of class C2, bounding a volume-connected interior domain. We assume that the surface gamma can be also require that different interior points of a rectangle under the specified mapping correspond to different points on the surface gamma. Now later, when I'll be talking about the point X, this usually means the point in a three-dimensional space outside of the surface at which we're trying to calculate the potential or hence the solution. The point Y represents the points on the surface gamma, which will be changing due to the normal vector at the point on the surface y on gamma can be explicitly written. Now, formula 6 is a formula for the surface integral of the first kind, how to go from it to the double integral. In addition, let's assume that the normal derivative of the surface gamma, the absolute value of it, is a double continuous function. So a class C2, that means that not only the continuous, but also its derivative and the second derivative. And we also assume that all interior points, all internal, the absolute value of the normal vector is also non-negative. From here, we partition the small rectangles, and the nodes are going to represent the central or the center points of these small rectangles. A simple layer potential for the Laplace equation with this partition divides to a sum of integrals over the small rectangles. Now, the integral inside of the expression 9 is usually referred to in literature as the canonical integral. So you can see here one of such examples. We introduce some notations in order to represent the values of certain functions in the center of these small rectangles. Now, when the step is getting smaller, so reaches 0 in a limit, there are two approaches I would like to focus here. Now, expression 11 is the so-called standard quadrature formula, which is the simplest way to calculate this double integral. Now, expression 10 is the attempt at accuracy by introducing more of the functions containing inside in the kernel of the integral. So, for example, in expression 10, you can see that up to the first derivative of the absolute value of the normal on the surface gamma is taken into account here. Now, the task at hand is to represent this quadrature rule as a main, addend, and the rest, the residue. Now, for the residue, the sigma 0, it can be shown that the estimate for it is big O from the sum of the steps on the big rectangle I was showing before. Now, the task at hand is now to calculate explicitly the canonical integral in the main addend of the quadrature rule called S0, and this is what I'm going to be talking about next. So about analytically finding the values of this integral. For that, you need to do a few things. First of all, you need to expand using the Taylor formula at the center of the points of small rectangles, and all the derivatives are going to be taken there. Separately, the denominator and the numerator of this expression. Now, introducing a few additional notations representing some linear combination of the aforementioned derivatives, you can write and also show that expressions for the first derivatives of the absolute value of the normal on the surface gamma can be also found using these expressions. Now, what it comes down to is that the main addend of the quadrature rule, 16, can be approximately found, and the integral big sigma and m is found in our work explicitly. Now you see it consists of a sum of integrals. The small, if I said sigma, I meant theta. So the small theta was calculated before in the 2019 paper. However, the rest of the integrals J1 and J2 needs to be addressed. Now for J1, the procedure is as follows. Now, three substitutions follow each other, the exponential, the hypergeometric one, and the linear, which divides this integral into a sum of these four mentioned integrals. Now, in order to calculate them, you need to look at this auxiliary integral J0, and while this integral is an integral you can find in a table or special books written for various analytical expressions of integrals, you do still need to pay attention about the values inside them, especially when you program it. Then, the mentioned integrals can be represented analytically or explicitly. Let me formulate the results of this approach in a theorem. Let gamma be a simple, smooth, closed surface, and it bounds a volumetrically simply connected interior domain. And let's assume that gamma admits the parameterization on a rectangle, the internal points of which, with the properties for the absolute value of the normal derivative and the potential density being a continuous function. Then the harmonic simple layer potential, when x does not lie on the surface itself, can be expressed as we did in equation 13. And for the residue addend, there is an estimate. Besides, for the main addend S0, there is a quadrature rule where all the integrals are calculated explicitly. Before I go to the numerical test, let me first show you the standard quadrature formula. The standard quadrature formula is obtained by simply replacing the canonical integral with the following approximation value at the center of the small rectangle. Now, it can be shown that such a formula does not provide a uniform approximation of the simple layer potential. That means that when the point x tends to the surface gamma and the steps are fixed, the error of the standard formula tends to infinity. Now, this is how you show this explicitly. Now, what we need to pay attention here, that in the numerical tests, I'll be comparing the improved quadrature formula I was talking about before with this main addend of the standard quadrature rule, represented as K0, and also shown here. Okay, now the numerical tests were performed when the surface gamma is a unit sphere. So you can see there are two parameters describing it. Here, introduce some external.
Sorry, Igor. I think we have problems to hear you well at this moment.
Equidistant are.
Sorry, Igor. Igor, can you hear me? Sorry,
Yeah,
Igor.
Yeah.
Excuse
I can
me.
hear you fine, yes.
We have problems to hear you well, I think. Maybe it's connection, something about that connection.
Maybe. I'm not sure I can fix that. So, okay, I'll read it. You can understand what I'm saying. So, for example, I'll read this sentence out here. Did you hear me when I said this sentence?
Right.
So I'm pretty sure there's a big delay, but I at least hope that with a delay, but you heard me.
Okay.
If you want, I can try to reconnect, but I'm not sure if that's necessary now, so I'll just wait.
Okay, thank you, Igor. Please continue then. Okay.
Oh, okay, I'll try. So if it happens again, feel free to stop me.
Thank you very much, Igor.
Now, testing was carried out when the surface gamma is a unit sphere. We had auxiliary spheres at some distance to it to calculate the layer potential and then compare it with the explicit value. So for unit sphere, you can write the solution explicitly because it's a sphere. Now, since the potential is known, we can compare the quadrature formulas to this explicit value and then find out the maximum relative error of all three quadrature rules. I'm going to show them step by step. So let's first look at the results for the standard quadrature formula. Table 1 shows first the distance where we calculated the simple layer potential. You can see that this distance is decreased by a magnitude each time. So this means that, for example, here, an auxiliary sphere external was at a distance of 0.001 to the unit sphere, on which the potential density is known and given. Now, here are the number of steps on each of the coordinates, and here are the maximum, and this is important. So these are the maximum values of error across the entire auxiliary sphere with, for example, this value of delta r, this distance from the unit sphere. Okay, now with that out of the way, let's see how the standard quadrature formula performs. First of all, you see that with the decrease of delta r, the maximum relative error of standard quadrature rule increases, tends to infinity. Of course, reducing the step helps, but nevertheless, this increase is very noticeable. Here's how the formula developed by my co-authors in 2019 shows itself here. You can see that the value of error does not really depend on the distance, does not depend on the distance to the surface. Now, this is really important because this is what should happen for the simple layer potential. It is a continuous function and should behave this way. It should not depend on the value of distance towards the surface. So this was already a very interesting result by my co-authors. Now, what I did with them is to improve this result. Now, if you, like I showed before, take into account the first derivatives of the absolute value of the normal vector, you can see that these formulas still retains the property of continuity, so it does not depend on the distance towards the surface, even that it's able to decrease the maximum relative error by sometimes a magnitude. But usually it's about 5 times lower for the unit sphere. Okay. Now the conclusions of this part is as follows. The standard quadrature formula tends to infinity. The formula of 2019 retains the property of continuity and uniform approximation, while showcasing the error of about big O from the step. So Ash represents the step on the coordinate u or v. Now the formula that takes into account the derivatives of the normal show the order of approximation, which is about big O from Ash to the power of 2. And we tested up to the distances of this order, depending on the step. Okay, now I'll continue. And I hope you can hear me well. Nevertheless, the second section represents the quadrature formula for the normal derivative of the simple layer potential. We need this formula to be able to solve the boundary value problem, to find the potential density. Now, here's how the normal derivative of a simple layer potential looks like. Once again, the idea is similar. We go from the surface integral of the first kind to a sum of double integrals on each of the small rectangle of the mapping I showed before. Now we can also see that the canonical integral in this case is different than it was for the simple layer potential itself. And still, under our assumption, the normal derivative is a continuous function on gamma. Now, another big difference is the fact that this function we are going to calculate on the surface gamma. Unlike the previous chapter I showed you, which was about calculations at some distance from the surface. So here we're going to be performing calculations on the surface. Okay, I hope that's clear. Now, there is a quadrature rule developed for the normal derivative as well. And as for the residue addend, I can say that it can be shown that if the steps tend to 0, this addend also tend to 0. So we need to, in a similar fashion, create a quadrature rule to calculate the main addend of this formula. When the point x lies in the integration domain. So as I've said before, on the surface. So it naturally happens once that your point x has come to one of the small rectangles to deal with this. And then all the rest of the cases are the second kind, which we talked about. You can see that the canonical integrals are very different here. The first, let's of whatever surfaces you care about. Okay, with that out of the way, we move to the second case. That is the calculation of this canonical integral when the point x is outside of the integration domain. So here the process is a bit similar. You start with substitutions. You need to deal with the integration over the coordinate v first, which we do. And then you end up with a certain expression, which again, by the way, involves this integral, which was luckily calculated before in the 2019 paper. What you need to take care about are these two, which are the same integrals, just from different values of big H here. So the step of the coordinate c. Okay, now this integral needs to be explicitly converted in a way that we can explicitly calculate it. Now what we do here is divide it by two smaller integrals, j1 and we're talking about them separately. So first of all, the integral j, both of these addends are interesting in their own sense. However, I should point out the expression 25. And this is the most interesting integral out of all of them, because polynomial under a square root. So you really need to watch out for all the different possibilities that can happen. Now, I will not be describing all of them because that's too long. I'll just mention the fact that if you look closely, you can also say that, well, there is a possibility for a singularity here, because if this polynomial equals to 0, or so connected to the discriminant. However, it can be shown that since the point x lies outside of the integration domain, The singularity does not happen here. We've dealt with the singularity in the first case, where we have integrated this specific case. Here we do not need to worry about it. But I'll wrap this up and just formulate the main result here, and then we'll go straight to numerical tests so that we can make it in time and see the actual solution of the boundary value problem. Okay, I'll stop here so you'll be able to see the theorem here. It's a bit similar to the theorem 1.1. However, this one we're talking about the normal derivative. Okay. Now you can see, as I've described previously, the sum of integrals is in the integration domain, so it's just one addend, and then all the rest are the second case for which we have calculated this integral explicitly. Actually, this one as well. So all of these expressions are okay. Let's continue. Now the standard also is, of course, for the normal derivative. It is quite similar in a way that all it does is just takes the values of the surface parameterization and the normal derivative in the nodes, so in the centers of the small rectangles, and then it just performs a summation of them. It's an okay approach, but if later someone is interested, I'll describe why this is not optimal and why do we try to kind of get away from this simple idea. Now, testing was once again carried out. Surface gamma is a unit sphere. I already repeat myself, but this time we're calculating the normal derivative now for, you do know the real or explicit value derivative. So here I'll be showing two tests. Oh, I think something. Probably someone connected. Okay, I'll continue.
Please continue. Is someone who wants to ask something, but questions at the end better. Yeah, please continue, Igor. Don't worry.
Oh, okay. The value of the normal derivative. Let's try to compare the two kinds of quadrature formulas, the standard one and the one that we call improved, so what we have developed. Now, let's look at test one. You can see that with this approach, we are able to achieve, once again, so I should mention this, that these numbers here represent the maximum absolute value of the quadrature formula across all the points on the unit sphere. So we took the maximum value of error and have inputted it here, just to clarify. And also the same done for the improved formula as well. Of error. That means that this formula can be useful in the numerical integral equations which arise in the process of solving the boundary value problems for the Laplace equation, which is exactly what we're going to do in the last section of this talk. It's the application. So the problem 30 I showed before. It's the external homogeneous gamma. We are looking for the solution in the form of a simple layer potential. Now, one important detail here I should mention is that in order to, let's say, conveniently solve the arising boundary integral equation, you need, so before we were using two separate numbers for the small rectangles, the small n and the small m. This is fine when you just deal with these functions itself. However, if you're trying to solve a boundary value problem, you do really need the continuous number. And so this is how you do it as an expression 32, how you go to the single number, which just wraps around each one of these uniquely, each one of these small rectangles. Now, this is important for the programming part. So the first stage, the Fredholm integral equation. It is known to be uniquely solvable. We need to go with the quadrature rule we have developed, or the standard quadrature rule if you choose so, to the system of linear algebraic equations with respect to the big M times big M values of the unknown potential density mu. So you can see here, this is rather standard stuff. We have arrived to a system of linear algebraic equations. We need to modify it a little bit in order to be able to perform the matrix inversion. So this is what I do in just some kind of zero out all the times when the diagonal elements do not include this addition as in the improved quadrature rule. So maybe it's easy if I show it in the matrix form. So we are looking to find out the values of the unknown function, the potential density right here. So we are able to write it in matrix form. And then what you need to do is to find this row here is to perform the matrix inversion here. And same for the standard quadrature formula, really. Okay. Now, were carried out once again. The surface gamma is a unit sphere. The first test is just the boundary condition being equal to 1 across the entire sphere. Now the explicit solution in this case is known. Also the potential density, same thing here, it is also known. And in test 2, we just try to make it a bit more interesting and maybe have the boundary function, so the boundary value oscillate a little bit, so just change across the entire see how these go to form in this condition. Okay, here are two tables which represent the thirsts of the solution. So here we once again have written the maximum absolute or mean absolute errors of potential density, just the potential density itself. So it's not yet the solution of the boundary value problem. We just try to determine the potential density, and the red color represents the improved quadrature formula, while the black one represents a standard approach. Okay, so we can see, like before, like in section 1.2, that the decrease is in place. However, the second stage of the solution will use the potential density in the simple layer potential itself, which is, as mentioned before, the solution to the boundary value problem, external one. Now you can see here, using auxiliary spheres again, because this is an external problem, we decrease the distance to the unit sphere. Solution, the maximum error using the improved quadrature formula does not really depend much on this. So this retains the property of continuity or in numerical methods, we rather say uniform of the quadrature formula. While, as before, the maximum absolute error of standard rule does depend on the distance, and it very noticeably increases when we get closer to the surface. Same in the test 2. So test 2 shows really the similar picture, though the boundary function now is oscillating. However, the property of continuity and uniform approximation is retained. Now, the conclusions for this is, the conclusions are the standard quadrature formula with a fixed step diverges when approaching the surface and gives orders of magnitude greater maximum absolute error than the proposed new quadrature formula. This is why at close ranges to the surface, this standard formula is not preferable to solve a boundary value problem for the Laplace equation. Now, the two new formulas I was talking about produce the first order of convergence of h, so the step, give uniform approximation, that means at any distance to the surface, according to numerical tests. According to numerical tests, this is the case. And also, one small detail here, while here first order of convergence, and we believe this is due to the fact that, remember, it is a two-stage process of solution, and the first stage involved involved finding the values of the potential density using the formula for the normal derivative. Now, these are the conclusions for my talk. I think we still have some minutes if anyone has any questions. Thank you very much.
Okay. Igor, spasibo za rozgovor. Dobro pošalovat na numero projekta. Thank you very much for your talk. So now we are open for questions.
Пожалуйста. Спасибо вам.
Okay. Maybe I can start maybe doing some questions, right? Because you have shown
Okay.
How to make this numerical procedure to solve the Laplace equation, right? But then my question is, if have you considered, let's say, the same problem, if instead of the Laplace equation, you consider, let's say, the Laplace operator plus some potential, like somehow some like one harmonic oscillator. If something like that also works, if your approach also works in that situation, or if you know some literature about that.
Yeah.
Can you hear me?
Question. So one of the first ideas that kind of prompt. Yeah, I can hear you just fine. Remember, it's just about 5 to 10. Yeah, we did think about also maybe expanding this method to, okay, for example, Poisson equation, or adding some additional add-ons in the right side of the equation. However, for now, this is more of a subject for future research. We have not tried this outside of the Laplace equation yet. So these formulas for now are specifically for the Laplace equation.
Okay, thank you. And maybe, if I may, maybe another question, if you can mention also another open problem in your setting.
If I understand correctly, you mean that the program that does these calculations, right?
Right.
Yeah, did all these, I will just go here real quick. So all these integrals I showed you were calculated explicitly. We used MATLAB for this, but really you can use whatever programming language you are familiar with. It doesn't really matter very much because it's mainly analytical expressions. So this is just a lot of tedious and careful writing down all these different formulas, example like one, for example. And yeah.
Okay. Thank you very much, Igor.
So yeah, of course we did. Yeah.
Okay. Thank you very much for, of course, your very nice presentation. So, and thank you for accepting
Thank
our
you.
invitation. So maybe we are in time to make some proof
Okay,
about the next talk of Professor Domingo Tarcia.
I think
Okay,
I will.
stop presenting. Spasiba, Igor. Spasiba.
Okay. Thank you very much.
Thank you. Profesor Tarcia, ¿cómo está? Bueno,
Muy bien, muy bien. Buenos días.
finalmente, qué bueno conocerlo. Está ahora en Argentina,
Sí, sí.
Argentina, en la Universidad Austral,
Australia, en Rosario, en la ciudad de Rosario.
en la ciudad de Rosario. Muy bien. Bueno, ¿qué tal el clima el día de hoy allá?
Bien. Tiempo primaveral más que de verano, pero
Sí.
bueno, con sol.
Sí, bueno, de Argentina tuve un muy buen profesor, Lázaro Rec, que estuvo primero en
Sí.
Venezuela.
En Venezuela, sí, lo conozco de nombre, sí.
Lázaro Rec, y bueno, ahora supongo estará en la Universidad de Buenos Aires, supongo. Sí. Bueno, muy bien, profesor. Muchas gracias por aceptar nuestra invitación. Si quieres, por favor, comparte tu pantalla
Sí.
para ver cómo trabaja tu presentación. Ok, perfecto. ¿Y puedes intentar mover las diapositivas para saber si... Ok, está muy bien. Ok, entonces, si me permites, déjame comunico con Julián de Dumedios, que está a cargo del streaming, y comenzamos en punto. Ok, Julián, ¿cómo estás, Julián? Listo, Julián. Entonces, para iniciar la siguiente charla, en punto, ¿sí? En 4 minutos.
Julián, buenos días. Regálanos un minuto que tenemos una dificultad técnica. Perdón.
Listo. Okay. Okay, thank you very much to all the participants who joined us. Our second talk of the conference is with great pleasure that I introduce to Professor Domingo Tarcia from the Universidad Austral in Rosario, Argentina. Professor Tarcia will talk about optimal control problems for elliptic variational and hemivariational inequalities and their asymptotic behaviors. So, Professor Tarcia, thank you very much, and please continue.
Thank you very much for the presentation, Duban. Thank you very much. I will present some mixed elliptic variational problem. But the important in this talk is to study some hemivariational inequality. Some comparison and asymptotic behavior when a parameter of the problem, the mixed elliptic problem, goes to infinity. Then I will study some optimal control problem, distributed optimal control problem, boundary optimal control problem, and simultaneous distributed and boundary optimal control problem for hemivariational inequality. We study some existence solution and the asymptotic behavior or the optimal control problems. Then some generalization. First, I will give you some preliminaries in order to define which is the hemivariational inequality. First, a definition for the local Lipschitz. It is well known, but we know some derivatives present and in the variational inequality, the Gateau derivative. But in this case, we will define the generalized Clark derivative as this definition. Here we have lambda goes to 0 and a goes to x. And the generalized gradient or subdifferential is defined by this property. Some properties is that the Clark derivative is positively homogeneous and additive. This is the property. This one is the more important to calculate the Clark derivative and some other property. For example, when we consider a quadratic function, the subdifferential is well well defined because it is a quadratic function. This is the subdifferential is the same as the classical derivative. Here we are the graphics, the graph of the function J and subdifferential of J. But here we have another function which in this case it is a function which is not convex. This is the more important condition in order to obtain the hemivariational inequality. And the subdifferential here is that. In the previous, here we have a quadratic and convex function, but in this case, the function is not convex. Here is a quadratic, but here is an exponential type of function. Now we study some mixed boundary, elliptic boundary problem. Here we have the Poisson equation. The domain is the boundary of the domain is have three disjoint portions, gamma 1, gamma 2, and gamma 3. And on gamma 1, we have here a Dirichlet condition. Here we have in gamma 2 a flux heat conduction condition, and on gamma 3 we have a Dirichlet condition. The condition on gamma 1 is in order to obtain the existent and unique solution is for that. But we have here another problem. In blue color, we have the difference. We have the same equation, the same boundary condition gamma 1 and gamma 2, but on gamma 3, we have this new condition, which is our problem P alpha. We will calculate the convergence when the parameter alpha goes to infinity. Here, G is the internal energy, B is temperature on gamma 3, the heat flux is a function of L2 gamma 2. Alpha is in heat transfer problem is the coefficient of heat transfer coefficient for the convective boundary condition. J is here is a no convex potential, but locally Lipschitz. And here is the subdifferential of J. For the problem P, this is classical. The formulation is given by this one, where A is the classical bilinear form, L is a linear functional, which is defined by inner product in omega and inner product in gamma 2. But for the problem P alpha, the formulation is given by this one. Later I will show as we can obtain this this hemivariation inequality. This is the new condition for the problem P alpha. Here I will show you as we can obtain the hemivariation inequality. We have here our problem here. Then we consider B is H1 and B0 is the space in each one with the condition 0 on the boundary gamma 1. Then we multiply this equation by B minus U. U is the solution. We have the integral. We have that. We can apply the green function, and we obtain here is 0, here this is Q, and here we have on gamma 3. But this condition, we have that we obtain this inequality because we use this condition. Minus derivative normal is in the subdifferential if and only if this condition is in the subdifferential of J. But for the definition of the Clark derivative, we have this, and then this derivative, this product with the normal derivative is verify this condition, and then we obtain this variational inequality, which is called hemivariational inequality, because here we have the derivative of Clark. When J is a convex or has a Gateau derivative, for example, si J is a convex function, then the problem P alpha is reduced to the variational inequality. It is a variational, elliptic variational inequality of second kind. This is, in this case, it is. But for the classical steady state heat conduction problem that I have studied in the past, in this case, the convex function is defined by this quadratic function. In this case, the variational equality is given by that. Then, in conclusion, see, if J is convex like this quadratic function, we have for the problem P alpha an elliptic variational equality. If J is only convex function, we have this new variational inequality. And if J is not convex, then we have this hemivariational inequality. For the classical problem, in the past, we have studied some property. This is for the case of J is a quadratic function. This is new, and we will generalize all the properties in the past for the hemivariational inequality. Then we obtain we consider the problem U infinity is the solution of the problem P, U alpha is the solution of the problem P alpha. In the classical case, we have some properties, and the more important is that the solution for the problem P alpha, for the variational problem P alpha, is convergent to U infinity in H1 as the parameter alpha goes to infinity. I remember that the parameter alpha is the heat transfer coefficient. From a physical point of view, the true condition on the boundary is not a Dirichlet condition, but the convective condition or Newton condition. But here we have that when the heat transfer coefficient is very large, then the solution converges to the solution with the Dirichlet condition. Here we have some results that we will study in the now. Some existent comparison, monotony, asymptotic, some example. In order to study the hemivariational inequality, we need some hypothesis for the function J. We have here some hypotheses. The more important is this condition here for the Clark derivative. This is hypothesis HG. Then, if this hypothesis is considered and L is a linear functional, then the hemivariational inequality for the problem P alpha has a solution, only an existent solution, but not the uniqueness. In general, if the hypothesis D is here, this is a general hypothesis because we don't know which is the function J. But if this condition is replaced by this new condition, which is called relaxed monotonicity condition, and we assume this small condition, then the problem has a unique solution. But here, this is in the book Vygotsky, Ochal, Sofonea in 2013. But this condition is not good for us because alpha, for us, it is important that alpha goes to infinity. Then this condition is not good for us. For alpha, for a small alpha, we have uniqueness, but for large alpha, we have not uniqueness. Then we must obtain the existence. Here is the proof, but I can pass because it is necessary to use very strong property for the functional. Here is the proof of this condition. It is the more important is to study to obtain a pseudo monotonic functional in order to obtain this property. In this case, for the surrogative property, we have a solution. We have some comparison property here. Here we have, in this case, we can obtain that the solution of the hemivariational inequality is less than B and also is less than the solution of U infinity, which is the solution of the elliptic variational problem. In this case, in order to prove this kind of probability, we use the idea in my previous paper because it is necessary to prove, for example, if I want to prove this condition, this inequality, then we consider the difference. We define W as the difference, and as W plus on gamma 1 is 0, it is important to prove that the positive part of the function W is 0. And then by using the some test function here, use the test function minus the positive part of W, we can study, we can obtain that this inequality as the bilinear form A is coercive in H1 with the condition 0 on gamma 1, then it is a norm, and in this case we obtain that the positive part is 0, and then we obtain this inequality. This inequality is for the solution of the hemivariational inequality. For the other inequality, this one, the method is similar. We obtain we consider the positive part, and then we obtain the same. This, in conclusion, we can apply the same property in the classical case for the hemivariational inequality by considering some different test function. Now, in order to obtain the monotonicity of the solution, it is necessary to define another hypothesis for the function J. This is a new hypothesis, which must be true for all C greater than 1. And in this case, we obtain this property, monotonicity property. For the proof is similar for the previous. We consider the difference. We obtain we use in the variation in the hemivariation inequality a function test, this function test, and then we obtain here is the hypothesis, is the new hypothesis. This is here, and then is the hypothesis we need, and then we obtain the inequality, and then we obtain the monotonicity property. In order to prove the conversion of the solution U alpha to solution U infinity, we need another hypothesis. With this property, we are in condition to generalize all the property for the classical problem. Then, with another property, we can prove that U alpha goes to converge to U infinity in H1. The proof is first, we prove that the sequence is bounded for all alpha. Then, by using the property of the Clark derivative, we prove that this is bounded by constant divide alpha. Then we can say that there exists a weak limit US 12 in H1. We can study that the US 12 is a solution of the variational inequality, and then we prove it's the convex, and so on. We can prove that the strong converse. Now, all the previous is for the system problem, for the problem P alpha or problem P. Now we will consider for this study, for these systems, we will consider some optimal control problem. Then, if we consider the control is the energy in the domain G. Then, for the problem, for the first problem, for the variational problem, maybe U infinity, we consider G is the solution, and then we can consider the optimal problem, which is find to a function in L2, the omega, such that minimize functional J, the capital J, which is defined in this equality. This is a classical cost function. In this case, zeta d is a new element in L2. M1 is a constant, and then here the control J is in the function, because for any G we can obtain the solution of the variational problem, and here we have also the norm of the control. Also, similarly, for the problem P alpha, we can obtain the same problem. We define, in this case, the G is dependent also in alpha. And the cost functional in this case is similar to the previous, but here we have the solution, a solution, because we haven't the uniqueness, but it's not so important to have a uniqueness in order to study all this optimal control. Here is a solution. Also, we can obtain a boundary optimal control problem. In this case, the control is the heat flux Q. Remember that the Q is the condition on gamma 2. Then for any heat flux Q in L2, the gamma 2, we consider UQ is the unique solution of the variational P. In this case, it's the same as before. For the boundary optimal control problem, we can define the same problem for the solution alpha. In this case, the difference is here we have a solution of the hemivariational inequality. Then we can also consider another optimal control problem, but here is a vector optimal control problem, because the control here is the energy and the heat flux. The energy in the domain and heat flux on the boundary. For that is a simultaneous optimal control problem, distributed and boundary condition. Here it is the same. For the problem when alpha is infinity, we consider the unique solution of the variational problem P. But for the problem when we consider the parameter alpha, then we can consider also a simultaneous optimal control problem, but here the definition is very similar, but here is the solution, a solution for the hemivariation problem P alpha. Here U depends on three parameters: alpha, which is the heat transfer, G, which is the energy, and Q is the heat flux. Then we will study the existence of solution for the distributed boundary and simultaneous distributed boundary control for alpha fixed. Then we will study the convergence when alpha goes to infinity for the problem G alpha, for the problem Q alpha, and for the problem G alpha Q alpha. And then we will study the convergence when alpha goes to infinity. And then here is the convergence of the system state to the system state corresponding to the limit case. Then, if we consider the hypothesis for the function J, small j, then we can prove that the distributed optimal control problem has a solution. The boundary optimal control problem has a solution, and the simultaneous optimal control problem has also a solution. Not unique, but also, the existence. Here there is a proof for the case C, for the case C, for the simultaneous, which is the technique. We can prove that the G is bounded, the Q is bounded, and the solution U is also bounded. For that, we can obtain the weakly limit F alpha, C alpha, and eta alpha, which is the weakly limit for the Qn, the Gn, and Un. Then eta alpha, which is the weakly limit here, satisfy this hemivariational inequality, and then we can say that this function is this one. And finally, we can obtain that the G alpha in this limit is less than the minimum, and then we obtain the solution. Then we can consider now the asymptotic behavior of the solution. In this case, we consider the hypothesis Hg and H1, and then when alpha goes to infinity, we can prove for the distributed optimal control problem that G alpha is convergent to the G in the optimal case. And the system is also convergent to the system infinity. For the boundary optimal control problem is the same. The optimal G plus alpha converges to the G plus optimal G plus, and the same for the system U alpha Q alpha. And also for the simultaneous distributed boundary optimal control problem. In this case, the vector is which depends on alpha goes to the limit strongly, and the same for the system of the problem. The proof is very similar to the previous. I prefer to pass this proof. There are some technical results to prove that. For the J, we have some hypotheses, but all this hypothesis is verified for the example I showed you before. Because we can put some hypothesis, but the set is big, the set is empty. Then we have some example to show that the hypothesis we have find is well. For example, for the case, the classical J is the quadratic function. All of these properties are verified. This is the proof, because in this case we can obtain the Clark derivative. In this case is the product. In this case we use the Clark derivative is the maximum. That I show you in the preliminary things. For the particular classical steady-state heat conduction problem for the quadratica, the optimal control problem were studied in these papers, Applied Math Optimization in 23. Some generalization that we have obtained is, for example, in this paper, we generalize the Laplacian for the PQ Laplacian. In this case, the Lichting equation is given by this one, where Laplacian P is defined for the classical divergence of gradient U P1 to gradient U. And the normal derivative is defined by this definition. And we can obtain the same properties. And another generalization is to obtain also the PQ Laplacian, but in this case, this derivative is a function which depends on the solution U, and L is have some property, and this is the more important condition in order to obtain the conversion. we need that this condition, this heat flash is 0 only when the variable S is equal to B. Another problem in progress is to study the numerical analysis by using the finite element method. In this case, we have the variational elliptic equality with the solution U infinity, as I showed you previously. And then for the problem P alpha, we have here variational inequality. We have here not uniqueness property. Here we have uniqueness. In the previous, I have shown you that the convergence when alpha goes to infinity is in this direction. This is, I have shown you here. But if we consider the numerical analysis, for this problem, we must consider the approximation of the variational inequality. And here we can consider the elliptic variational equality. Here we have uniqueness, but here we have a not uniqueness property. But we can prove the following. This solution is convergent to this one when H goes to 0. H is the parameter of finite element method. Here, this problem is convergent to this one when H goes to 0. The new property, the solution, this solution converges to this solution when alpha goes to infinity. This is very similar to this one. This is the continuous problem, but this is the convergence for the discrete problem. The another property is when we consider this diagonal convergence is in the double limit when H alpha goes to 0 plus infinity. Then this is I have shown you at the beginning. This was studied in one previous paper of mine, and this is new in this work in progress. The limit one L1 is I have proved in IFIP 2015. The limit 2 was proved that I showed you previously in Applied Math Optimization 2021, and the 3 limit L3, 4, and 5 are new. And for the particular case, for the quadratic case, all limited, the continuous and discrete problem was proved in this article. Then, as a conclusion, we can say that for the class generalized gradient, we have studied elliptic variation inequality and optimal control problem in 3 different cases: distributed for the energy, the boundary for the heat flux, and the distributed boundary for the energy and heat flux. Then we have proof existence of a solution for the ME variational inequality. We remark that we have no uniqueness for the ME variational problem. And then we have obtained the asymptotic behavior when the parameter alpha goes to infinity. Some reference, I can say you the presentation here. Thank you very much.
Okay. Professor Tarsia, thank you very much for your very nice talk. So now we are receiving questions. So does anyone has questions for Professor Tarsia? Maybe Santiago? Maybe. Santiago, are you there?
Yes, I'm here.
Okay.
Just a second.
Yes. Please proceed.
Yeah, Professor Tarsia, thank you very much for your talk. Rather than a question, I have a curiosity. At some point, if you can go back to the slide with title Asymptotic Behavior of Solutions. You mentioned one hypothesis there, H1, I think.
Here.
Yeah, exactly. So I was wondering whether this hypothesis is optimal in some sense. Have you thought about this, maybe?
This condition is sufficient to prove our result. It's sufficient. I don't know if the optimal condition, but for us is the sufficient condition. I think that we need that on the boundary, the gamma 3, it is necessary that we have zero condition. It's like in the last. Here we have generalized the problem. Here we have alpha, which must go to infinity. But here is the function which depends on x and the solution. But this condition is very important in order to obtain the converse.
Okay.
The first condition, H1, is similar to this one.
Yeah, that's clear. Thank you.
No,
Okay, thank you very much. Does anyone Thank you. Does anyone have more questions for Professor Domingo Tarsia? Maybe, okay. Maybe I have a question, Professor Tarsia, but it's related with one of the first slides when you formulate your problems, right?
Where? Excuse me.
It was in one of the early slides, first slides. I think the slides where you were describing the conditions to satisfy for your functions b, g, and etc. and q, I think.
The definition of the problem?
Yes, I think. Let me see, maybe go. Because there my question is, here, the next one, the next slide. Here, right, because my question here is about the order of regularity that you consider for the function b, right? Here you consider b to be in this Sobolev space edge with the power half, right? And then,
Yes, this
right,
is
and then my question, is why to consider half as the precise order of regularity in this case?
because it's for one, the solution is in H1, in H1, but here is the boundary condition. Then for the truss Sobolev space.
Okay.
This is
Okay.
but
So-
in more property we have a study. B is a constant for some in order to study our property, we use B is a constant, but in general for the elliptic problem we need that because P is the truss or a function of H1.
Okay, right. And then so the reason, if I understand well, is because the one requires the trace Sobolev theorem, right?
Yeah.
You have a function in a domain, and then with order of regularity half plus something, then you have the restriction well defined and so on, right? Okay. No, that was my question. Does anyone has more questions for Professor Domingo Tarcia? It seems that the people were very happy in your presentation. That was very clear, of course. So thank you very much, Professor
Thank you very much.
Tarcia, and thank you for accepting our invitation. So maybe we can wait a couple of minutes. Now, I am going to pass my chairing the duties to Alexandra Garcia, who will be the chair for the session of Professor Bienvenido Barraza.
Thank you, Duan. Gracias.
Quizás comencemos a las 5 en punto. Okay. But
Gracias.
déjame de pronto preguntarle al profesor Bienvenido. Profesor Bienvenido.
Okay. Welcome to everyone to this talk. It's a pleasure for me to introduce Professor Bienvenido Barraza, who will talk about analysis of the exponential stability of a beam stream beam transmission problems from Universidad del Norte in Barranquilla. So please continue, Professor.
Thank you
so much.
Thank you for the presentation. Hello, everyone. First of all, I would like to thank the organizing committee for inviting me to participate in this important mathematics event. It's a pleasure to be here and present some results of transmission problems for beam string beam system. These results are from joint work with Jairo Hernandez and Jonathan Gonzalez from Universidad del Norte. This talk is organized as follows. First, an introduction, then the well-posedness of the problems, then the exponential stability for the solution of the system, and finally some open questions. Before I begin with the introduction, I would like to say that I will not present the details for the proof of exponential stability. I will concentrate in the abstract formulation of the Cauchy problem as Cauchy problem and the well-posedness for this problem. The study of transmission problem often referred to analysis of model involving different media or different laws in separate subregions. Such work were started by the Italian mathematician Mauro Piccone in 1954, who studied transmission problem arising in the theory of elasticity. In the last few years, very research are investigates transmission problem due to several applications in fields of physics, biology, material science, industry, etc. This is in particular relevant for mathematical model associated with composite materials. For example, in recent advance in material science in modern technology have provided new means for research engineers and scientists to suppress vibration for multi-link structures using or applying local or total damping on one part of these multi-link structures. This multi-link structure consisting in connected flexible elements such as beams, string, plates, membrane, or shells. They have many applications in engineering areas such as antenna, robot arms, solar panels, aircraft, bridge, buildings, and so on. For example, for the wings of an airplane, is built from different materials to reduce the vibration caused by wind or other external force. Other example is the foundation of buildings can be designed from different materials using intelligent materials, advanced material, and technology to minimize vibration and resist resist external force such as earthquakes. The structure that we will consider in this talk is this. The structure has three parts. The first part is a beam, the second part is a string, and the third part is a beam. In the first beam, we have is fixed in the endpoint L0. That means the U satisfies a clamp Dirichlet boundary condition in this point. For the second beam, that is fixed in the endpoint L3. That means that W satisfies Dirichlet boundary condition in this point. We want that the structure does not break. Therefore, we suppose that U at point L1 is equal to V in this point, and V at point L2 is equal to W in this point. The points L1 and L2 are the interface point. L0 and L3 are the end points for this structure. We will consider damping or no structural damping on the beams, first beam and in the second beams. If for the string, we will consider an frictional damping or a Kelvin-Foy damping. Some results that you can find in the literature are the following. For example, in this problem, we have strings with local Kelvin-Foy inside of the string. Liu and Liu in 1988 showed that the solution of this problem is not exponential stable. Then Liu and Zheng in 1989 considered a string with frictional local damping inside of the string. They showed that the solution of this problem is exponential stable. Then we have a string with local Kelvin-Foy damping, but the difference with the first problem is that here the damping is a small function. In this case, Sands proved that the solution of this problem is exponential stable. Then we have a system composed with three different materials. The first part has Kelvin-Foy damping. The second part is an elastic string without damping. And the third part is acting and frictional damping. Alves Muñoz Rivera et al. Showed that the solution of this problem is exponentially stable when the Kelvin-Foy damping is not in the center of the material. Tanhasini in 2015 considered this system being string, where on the string there is a local Kelvin-Foy damping. He showed that the solution of this system is not exponential stable, but it is polynomial stable. Finally, Li, Han, and Su in 2018 considered a beam string system, but the string is acting on total frictional damping. They showed that the solution of the system is exponential stable. Also, you can see that in either case, the structure is stable. In another case, the structure is not stable. Then in this talk, we will consider this problem. We have present in this talk 5 problems. The first problem is this when in the first beam we have structural damping. In this equation you represent the vertical displace, the H point of the beam. We coordinate X at time t. This row 1 represents the presence of ascent from frictional damping of this beam. In this case, row 1 is a constant, a positive constant. In the second part, we have a string where V in equation 2 represent the vertical displacement of H points of the beam. Coordinate X at the time t. Beta in this case is a positive constant, that represents that on the string is acting frictional damping. And for this equation, in the third equation we have the W. In W represent the vertical displacement of H points of the second beam, and rho 2 is a positive constant. That means that on the second beam we have a structural damping. For this problem, under certain boundary condition and transmission condition, we have established that the solution of this system is exponential stable. The second problem, we have the same structure, but on the beams there are no structural damping, but on the string we have the frictional damping. In this case, beta is a positive constant. For this case, and for the same boundary condition and transmission condition for the problem 1, we have in this case that the solution of the system is exponential stable too. The third problem is similar to the second problem, but in this case, the frictional damping is a local damping because beta is in a infinity function on I2. That means that beta can be 0 in one part of the string. For this case, under the same boundary condition and transmission condition for the problem 1 and 2, we established that the solution of this system is exponential stable. That was a good result because in the problem 2 we have a global damping on the string. In the problem 3 we have only local frictional damping on the string without damping on the beams. For the fourth problem, we have changed this frictional damping by a Kelvin-Foy damping. Kappa null is a coefficient, certain local Kelvin-Foy damping, under an additional condition. That condition means so that in the second beam, in the point L3, the beam is clamped And the point L2, we have the being a simple support. Or we say that in the point L2, W satisfies hinge boundary condition. That is that in this point, W in L W is equal to zero. And the second derivative of W is equal to zero. For this problem, on certain K0, we establish that this problem is not exponential stable. But we want to have a structure that the system is exponentially stable over the time. Therefore, in the next problem, we will consider certain Kelvin point damping and additional boundary condition. In this case, we have the second beam in this interface point is simple support, but in the first beam in this interface point L1, the beam is simple support too. That means that U in L1 is equal to 0, and the second derivative of U in L1 is equal to 0. Under this condition, and we have for certain coefficient kappa that the solution of the system is exponential stable. That was the result that you can find in two papers. In paper that was published in 2022, you find the detail for the problem 1 and 2, and the details for the 3, 4, and 5 problems can you find in a paper that was published this year. We can resume the 5 problem in these 3 equations with the following boundary condition. This is transmission condition. This condition is that means that the first beam is clamped in the point L0. That's in the clamp Dirichlet boundary condition that are equal to 0. And the second beam is clamped in the point L3. That's in the clamp Dirichlet boundary condition for the second beam in the point L3. That are boundary condition 2 in the point L1 and L2. That means that in this point the beams has not been the moment. This transmission condition is a continuity transmission because we want that the structure does not break. That's where the condition that is explained before. Of course, for dynamic partial differential equation, we have a standard initial condition. Now we want to write this problem as Rata-Cauchy problem. Therefore, we find midden base space. For the bases, identify the base space, we begin with the energy for the whole structure. So we consider the first beam, V for the string, and W for the second beam. The derivative, the temporal derivative of the energy is this expression. There you can see that when one from this coefficient is different to 0, then the derivative is negative, and therefore the energy of the system decreases over the time. That means that the energy is dissipative. But we want analyze or we want that the energy satisfy this estimate here. That is when the energy satisfies this estimation, we say that the energy decay exponentially stable, or the energy is exponentially stable. That is the idea for the 5 problem, except the 4 problem that it is not exponential stable. For the abstract formulation as a Cauchy problem, we denote U as U1, V as V1, W as W1. The temporal derivative of U as U2, the temporal derivative of V as V2, and the temporal derivative of W as W2. When we denote U capital as a vector with the 3 first components U1, V1, and W1, and the second 3 component as U2, V2, and W2, we have the following. For example, that the dot U1 dot represent the temporal derivative of U1, but that is U2. That is U2. That is the temporal derivative of V1, but that is V2, etc. In this point, that is the temporal derivative of U2. The temporal derivative of U2 is the second derivative of U respect the time. That due to the first equation of the system, that is the equation of the first being. The temporal derivative of V2 is the second derivative of V. Due to the equation of the string, we have this equality. In the same way, we have this relation for the partial derivative of W2. Then we see that the temporal derivative of U capital is these columns. This column is equal to this column. Therefore, when U is so, we can write our system as this Cauchy problem that you see here with this initial condition. Also, that is an approximation from the abstract formulation our problems, but we must precise the definition, the domain from the operator A. Then we define the following function space. This space is the sole space H2 on the interval A1. In this space, the same subspace of this sole space with this condition. These conditions are the same boundary condition for the first bind. For this subspace of this sole space on the A3, we have this condition, and these conditions are the boundary condition for the second bind at point L3. These spaces are equipped with these inner products. We can show that this space with the norm induced norm from this inner product are equivalent to the standard or the usual norm in this sole space. Then we define the space H as time subspace of this product space, but we introduce here the continuity transmission condition. That is that the U in L1 is equal to V1 in LU, and V in L2 is equal to W in L2. Then we define this product space, and then with the standard or the usual inner product, assume the inner product in the Hilbert space. And then we define this H Italy as this space product. Of course, with the standard or usual norm, that's inner product, that is the inner product in H, and that is the inner product in L. You can see here that for the bin, for U, U is in this space, then U has two distributional derivatives, but in the transmission condition 29, U1 has three derivatives at point L2. Therefore, we must introduce a definition of the transmission condition in a weight sense. That is, we say that U satisfies the boundary condition and the transmission condition in the weight sense when this equality holds. And then we can precise the definition of the operator H with this domain. The operator is defined as before. Also, from this operator, we prove that when we have a solution for our abstract taco chip problem in this domain, the elliptic regularity implies that U1 is in half-4 and V1 is in half-2 and W1 is in half-4, excuse me, and therefore the boundary and transmission condition holds in the classical sense. For the other three problems, the problem 3, 4, and 5, we define in similar ways of the problem 2 and 1. But for the problem 4, we introduce this condition that the second being in the point L2 is equal to 0. And for the problem 5, we introduce this two boundary condition that the V1 in L2 is equal to 0 and W in L2 is equal to 0. Then we define again the inner product, the Hilbert space, H, and the operator H in the same way. And then we have shown this abstract Cauchy problem for our initial system. H is 1p25. That is the standard definition for classical solution for the problem DT3. The first theorem of this talk is that the operator H is the infinitesimal generator of a strongly continuous semigroup of contraction on the Hilbert space H. For the proofs, we show that the operator is dissipative. That is, the real part of this inner product is less than or equal to 0. That is because we calculate this expression and we obtain that. You can see that this is less or equal to 0. Then we show that the operator, the identity minus the operator H is surjective, but that is a consequence for the last Milgram lemma. But then due to 1 and 2, we have that the domain of H is dense in the basis space H. The reason is because the H is a Hilbert space, because the H is dissipative and this operator is surjective. Then the standard theory of semigroup theory implies that this operator is the generator of a strongly continuous semigroup due to the Lumar-Phillips theorem. That is the idea of the proof of this theorem. Therefore, we have that our problem, abstract problem, DT3 is close-postness. That is that there is a unique classical solution U in this space which depends continually on the initial data U0. For the exponential stability, we define first we define the energy of the solution. That is related with the energy that before I have defined in the second slide, and that is the norm square of the solution, time and half. That is given by this expression, and the time derivative of the energy is that. We showed that for the problem 1, that's when rho is positive, rho 1, rho 2, and beta are positive, the energy of the solution decays exponentially at the time or over the time. That is, the systematon holds. I have improved. Ich möchte I don't present the details for the proof. It gives no eine. It gives only idea for this proof. In this case, we define this function f. We derive the time derivative of this expression. This function satisfies this equality. Then we define an auxiliary functions with f and the energy. In this constant, Z right is initially an arbitrary constant, but not calculation. We obtain that this L function that I was defining here that is the Lyapunov function, satisfies this estimation. That means that the energy and the Lyapunov function are equivalent, and the Lyapunov function satisfies this estimation by Gromwell inequality. We have this estimation. Therefore, the energy satisfies of this similar estimation. That is, therefore, the energy of the problem 1 decays exponentially over the time. That's it for the first problem. For the second problem, we use the domain frequency method. That is a result of Gerhardt, Proust, and Wang. This result say that let T be a strongly continually semigroup of contraction of a Hilbert space generated by an operator A. Then the semigroup is exponentially stable if the imaginary time is a subject of the resolvent set of the operator A, and the resolvent operator is bounded for all lambda in R. The result for this problem 2 is this. In this case, rho 1 and rho 2 are equal to 0 and beta is positive. Then the semigroup generated by A1 is exponentially stable. I don't give the proof here because for the problem we have a similar proof. In this case, I don't have a Kelvin-Foy damping on the spring, but we have a frictional damping. Here beta is an element in the Sobolev space with one distributional divided. This beta is a function in L infinity, so that the derivative is a function in L infinity. It's not negative, but it's positive in an interval inside in the interval L1 to L2. For this local frictional damping, we have this result. This result is that under this condition, the semigroup generated by the operator A3 is exponentially stable. I have here the online of the proof. We show first that this is a subject of this resolvent set. Then we show that this is in a constant. For the proof, we assume that this is false. Then there are sequence lambda on U, so that satisfies this condition for lambda go again infinity, and the norm of UN is equal to 1. Then and we have to this convergence. This convergence. Then we show that this condition leads to the contradiction that the norm from UN in H3 go to 0. That is that each component of this norm go to 0. For this, we define that Sn. Use the definition of the operator E3. So we obtain this equation. Then from the dissipative of H3, we obtain this convergence, but this convergence are needs on the whole L1 on L2. These convergence are only in one part of the Gauss interval. Then we introduce an equation in other equation. We use partial integration, Cauchy-Schwarz inequality, Young inequality, Trace theorem, technical calculation. We obtain this estimate, this convergence. This convergence trade or deal with the transmission point, the string and the pins in the transmission point. With these results, we obtain that this convergence in color red in term that belong to the norm from U capital. Therefore, we show that the norm from U capital go to 0. And that is a contradiction because the norm from UN is equal to 1. In this form, we prove that the third problem is exponential or had exponential stability. Now, for the problem 4, we had lack of exponential stability. In this case, we have a local temperature damping that is constant in the inner from one part for the interval L2. With satisfying this condition, we have a sequence so that this estimation does not hold. Therefore, we have this. In this case, the problem is not exponentially stable. The details of the proof are in paper in the literature. For the problem 5, we have this local Kelvin-Foy damping and function kappa satisfying this all of this condition is like a dash. And for this Kelvin Foy damping, we have that the problem phi is exponential stable. Also, we have a technical proof in the article. Therefore, I want not show here in this talk. Now, open question. The third question is what happens when the exponential stability of the whole structure if the Kelvin Foy damping on the string is given by a small function is supported in the inner of the interval I2. That means here for this case the damping is acting in close to the interface point L1 and L2 is 0 in the inner of the interval I1. The question is when the support of kappa is in the inner. If here is and kappa is null in here in this interval and in this interval. That is the first question. What happened in this case? The second question is what will happen when to the exponential stability of the entire structure when the frictional or Kelvin Foy damping is replaced by a total or global thermal effect on the string. Also, we want to change this to damping, frictional or Kelvin Foy damping by a local thermal effect on the string. And the last question is what happened to the asymptotic behavior of the system of the solution over the time when a delay or a memory on the string is considered. Also, that's the same question that are open for us, and there are the two papers. In the first paper, you find the type for problem 1 and 2. And the second paper, you find the type for the problem 3, 4, and 5. And there are other literature that is here mentioned. Thank you very much. Thank you very much.
Okay, thank you, Professor. Bienvenido. Now is the time for the question. Thank you so much for your interesting talk. Okay. Someone, does anyone has question? Okay, Tobias. Continue.
Can you hear me well?
Yes, I heard.
Profesor Primitivo.
Hello, Tobias.
Good morning.
Good morning.
Hi, everyone. I just have one question. I would like to know if you have, from the point of view, from the numerical point of view, do you have any approach to solving or for solving this kind of systems?
No, we don't have an approach for this problem.
I see.
Sorry.
Ya, bom. Muito obrigado. Muchas gracias.
No,
Thank you.
The one? Yes.
Yes. Okay, Professor, bienvenido a Raza. Thank you very much for your very nice talk, of course. My question is, is the following. If you maybe can say something about the main difficulties in extending, let's say, your work to membranes or plates to more high-dimensional setting.
Yeah, good question. For high-dimensional space, there are results that hold in one-dimensional, but does not hold in two or three-dimensional space. That is difficult because the structure can they have that can deflect in different way, yeah, in different direction. Though there are we have results for two-dimensional setting for plates coupled with membrane, but our damping are total damping or on the beam or on the spring, but we don't deal not yet with local damping on the whole structure.
Okay. Thank you very much.
Thank you very
much.
Thank you.
More question for the professor? Anyone? Okay, Professor, I have a question. In the slide 9, what are the conditions on the beta function?
Here?
Yes. Say that beta, yes.
Yeah,
The function
that is for
beta.
the problem 3. For the problem 3, that's one moment. That
Okay. Oh. Yeah, perfect.
that is in general conditions. Beta moves positive in one part of the string.
Thank you, Professor.
Okay.
Okay. More question? Okay, Professor. Thank you so much for accept our invitation. Yeah. Now.
Thank you too.
Yeah. Now we continue with the next professor.
Okay. Thank you.
Thank you. Bye. Yeah.
Bye.
Professor Miguel Luque is there?
Hola, espero que se encuentren bien. Bueno, no soy profesor, soy estudiante.
No hay problema.
Okay. Okay. Thank you very much to all the participants who join us in this the fourth day of the conference. It's with great pleasure that I introduce to a PhD student from Colombia, Miguel Santiago Luque Casallas from the Universidad Distrital Francisco José de Caldas. His talk will be in Spanish, and he will talk about continuity and compactness of weighted composition operators acting on sequence spaces. So, Miguel, puedes iniciar.
Ok, vale, gracias, Duan. Bueno, espero que todos estén bien. Hoy les voy a hablar sobre la continuidad y compacidad de operadores de composición con peso actuando en espacios de sucesiones. Pues decimos que este es un tema del análisis funcional, pues una disciplina rica y diversa que ofrece herramientas muy poderosas para abordar problemas en matemáticas y ciencias aplicadas. También decimos que la capacidad que tiene esta rama para tratar con espacios infinitos y operadores lineales, pues ha abierto nuevas vías de investigación y solución en áreas tan variadas como lo es la física, la ingeniería y demás. Pues en el análisis funcional, el estudio de operadores, como vemos, sus propiedades como la continuidad, la compacidad, el espectro de operadores lineales, pues ayuda a comprender cómo los sistemas evolucionan con el tiempo y cómo se pueden aproximar soluciones a problemas complejos. Es por eso que vamos a definir un operador, y caracterizar su compacidad y continuidad. Pero para esto, pues vamos a definir primero nuestro espacio al cual vamos a trabajar, que se llama el espacio de sucesiones de Lorentz, pero antes requerimos de dos definiciones muy fundamentales para llegar allí, que se llama la función de distribución y el reordenamiento decreciente. Entonces, la función de distribución de una sucesión real o complejo, también se puede llamar para los números complejos, se nota como numeral sub x, y esta cuenta cuántos elementos de la sucesión tienen un valor absoluto mayor que un lambda dado. Esta función incluso puede alcanzar valores de más infinitos si existen infinitos elementos que cumplan dicha condición, ¿sí? Acá a simple vista pues podemos observar que dichas sucesiones que su valor que su función de distribución tiene infinitos valores son aquellas sucesiones que no son acotadas. Pues podemos considerar la sucesión x de n igual a n y pues su función de distribución siempre va a ser infinito. Otro ejemplo, pues si consideramos la sucesión 1 sobre n más 1, pues esta sucesión va a estar acotada superiormente por un medio, y pues cualquier lambda superior o igual a un medio pues hace que esta relación entre el valor absoluto y lambda sea vacía, por lo que el número de elementos que satisfacen esta condición es 0. Sin embargo, si lambda está entre 0 y un medio, pues esta relación entre el valor absoluto es equivalente a n menor que 1 sobre lambda menos 1. Y pues la cantidad de elementos de esta sucesión que está por encima de cierto lambda, pues va a estar determinado por la parte entera de 1 sobre lambda menos 1. Este cierto lambda tiene que estar dentro de este intervalo, ¿vale? Entonces la función de distribución queda caracterizada de esta forma. Posterior a eso, pues definimos la función de distribución, definimos algunas propiedades de la función de distribución. Entonces decimos que entre las propiedades tenemos que la función de distribución es una función decreciente. Si una sucesión está compuesta por valores tales que su valor absoluto son todos menores o iguales a los de otra sucesión, entonces contendrá menos elementos. Entonces esta sucesión contendrá menos elementos que excedan cierto umbral comparados con los de la otra sucesión. También hay otra propiedad, la aditividad, que cuando sumamos dos sucesiones, pues el número de elementos que superan un cierto umbral en la sucesión combinada, pues no será mayor que la suma de los elementos que superan ese umbral por separado en cada una de las sucesiones respectivamente. Ahora sí, definimos el reordenamiento decreciente a partir de la función de distribución. pues la idea acá intuitiva de esta definición es reordenar el valor absoluto de los elementos de una sucesión de manera decreciente. Entonces, el reordenamiento decreciente de una sucesión real se denota como X estrella de n, y pues esta toma un valor en los naturales y devuelve un valor en el intervalo cerrado 0 infinito. ¿Y que cómo calculamos X estrella de n? Pues encontramos el lambda más pequeño, tal que hay n-1 elementos o menos elementos de la sucesión X, tal que su valor absoluto son mayores a lambda. También es importante extender esta definición para cualquier real positivo. Claro que si T es un real positivo, entonces, y que además es mayor o igual que n-1 y menor que n, entonces esta va a coincidir con el ordenamiento decreciente de X estrella n igual a X estrella de T. Acá no lo coloqué, pero es así. Como ejemplo, pues consideremos la sucesión n sobre n más 1. Entonces, si lambda, acá podemos, visualmente, pues podemos ubicar a lambda como una recta horizontal en el plano. Si lambda es mayor que 1, pues la función de distribución va a ser igual a 0, porque no hay elementos por encima de esa cota con el cual podemos comparar. Y si lambda está entre 0 y 1, pues siempre podemos encontrar infinitos valores que están por encima de lambda. Entonces, para que nosotros podamos comparar la función de distribución con respecto a un natural incluido el 0, pues necesariamente lambda debe ser mayor o igual a 1, ¿verdad? Y en ese sentido, pues podemos decir que X estrella de n pues va a ser igual al ínfimo de este intervalo, que va a ser igual a 1, y esto es para todo natural. Ok, entonces acá me faltó poner algunas propiedades, pero las menciono así por encima, y decimos que el reordenamiento decreciente coincide con la misma sucesión. Si una sucesión es decreciente, pues su reordenamiento decreciente coincide con la misma sucesión. Además, si X asterisco de 1 es finito, como en este ejemplo, entonces esta coincide con la norma infinito de la sucesión. Esto es que la sucesión es acotada. También hay otras propiedades como la monotonía. Si tenemos que una sucesión domina a otra, pues su reordenamiento decreciente también domina. Hay una cierta propiedad de invertibilidad que relaciona el reordenamiento decreciente con la función de distribución que la define, ¿sí? Y por último, también existe una propiedad que es muy importante, que es la subaditividad del reordenamiento decreciente, porque, entre otras cosas, hay que probar que el espacio de Lorentz es un espacio vectorial. Entonces, una vez habiendo definido el reordenamiento decreciente y sus propiedades, entonces el espacio de Lorentz queda caracterizado por aquella sucesión para la cual su reordenamiento decreciente cumple con estas dos propiedades o estas dos condiciones de acá que son finitas, ¿sí? Diremos que una sucesión pertenece a este espacio de Lorentz que se denota como LPQ, solo si su reordenamiento decreciente está en un cierto LPQ con peso. Acá podemos observar que la sucesión que multiplica el reordenamiento decreciente de la sucesión cumple con una condición que se llama delta 2. Entonces, con un profesor, hace poco hicimos una investigación y generalizamos estos espacios de Lorentz para aquellos pesos que tienen la condición delta 2. Si se preguntan cuál es la condición delta 2, es que si una sucesión cumple con esa condición, bueno, en nuestro caso tiene que ser una sucesión creciente. Y además existe una constante K tal que cumple con esta relación que se muestra acá. Entonces nosotros generalizamos ese espacio con esta condición. Bueno, y como ejemplo de este espacio vectorial, pues están las sucesiones canónicas. Yo creo que todo aquel que haya hecho una investigación en análisis funcional sabrá que las sucesiones canónicas no pueden faltar en esta línea de la investigación. Entonces se define como n es su n de k igual a 1 si k es igual a n y 0 en otro caso, ¿sí? Entonces, al momento de evaluar esa sucesión en dicha serie y en el supremo, pues en ambos casos siempre nos va a dar igual a 1. Por lo tanto, pues estas sucesiones pertenecen a este espacio de Lorentz. Otras propiedades, pues bueno, tenemos que este espacio es un espacio vectorial. De hecho, esta relación de acá, pues es una cuasinorma, es decir, que es una función que va del espacio de Lorentz a los reales, de tal manera pues que cumple la no negatividad, la homogeneidad, y pues a diferencia de la desigualdad triangular, pues no la cumple, solo que garantizamos la existencia de una constante en términos de P y Q, de tal manera que multiplica el costado derecho de la desigualdad, haciendo que dicha relación se preserve o se cumpla. Y decimos que este espacio es sólido. Es decir, que si una sucesión en el espacio de Lorentz domina otra sucesión, entonces la sucesión no dominante también está en el espacio de Lorentz. Y además pues se preserva la desigualdad entre las cuasinormas de dichas sucesiones. Por último, este espacio es cuasi completo para P y Q con estas condiciones, ¿sí? Como bien sabes, pues esta relación no es una norma porque no satisface la desigualdad triangular. Sin embargo, se puede definir una norma equivalente a esta cuasinorma, y en este sentido decimos que el espacio estará cuasi completo en el sentido de que toda sucesión de Cauchy converge en ese mismo espacio. Bueno, acá hablando un poco de cuál sería dicha norma equivalente a esta cuasinorma, pues se construye a partir de la sucesión maximal, que pues se caracteriza por tener el ordenamiento decreciente y por estar en esta sumatoria finita.
Perdón, Miguel, ¿puedes desmutearte? Disculpa, que...
ok.
Desmutearte solamente, sí. Disculpa, es que había ruido en la sala, entonces muteamos los participantes y a ti también, disculpa. Pero continúa, por favor.
¿Pero eso fue hace poco o...?
Ahora, ajá.
Ok, entonces, hablando un poco sobre esta norma que es equivalente a dicha cuasinorma, pues se construye a partir de la sucesión maximal, que se define como esta sumatoria finita y que tiene en cuenta el reordenamiento decreciente de la sucesión. Y la norma pues se define muy análogo a cómo se define el espacio de Lorentz. Entonces diremos que que es una norma y que es completo. Probar la completitud acá es un poco complicado porque pues requiere un poco de teoría de la medida. Y pues observemos que la tripla de los números naturales y partes de los naturales y nuestra función de medida, que en nuestro caso es la función de distribución, pues forman un espacio de medida. Y entonces así tenemos que cualquier sucesión sobre los naturales si es de Cauchy en media, entonces esta contiene una subsucesión que es convergente. Y también utilizando el lema de Fatou, que nos dice que podemos intercambiar límites entre las sumatorias. Entonces esto nos permite verificar que este espacio es completo. Otro resultado importante es el de Takashi y Aoki, que nos dice que si tenemos un espacio cuasinormado, entonces podemos garantizar la existencia de un P en este intervalo y una cuasinorma equivalente a esta cuasinorma, pero que cumple con esta condición, ¿sí? Que al momento de elevarla a la P, pues que se convierte en una norma. Y pues este espacio pues se convierte en este espacio con respecto a esta métrica P, pues se convierte en un espacio métrico, perdón, la redundancia. Luego el estudio de la convergencia y las propiedades topológicas en un espacio cuasi normado, pues sería a partir del espacio métrico con respecto a la métrica de P. Entonces, en ese sentido, diremos que el espacio, este espacio cuasi normado, pues será cuasi completo en el sentido de que si este espacio métrico es completo. Listo. Entonces, acá pasamos a recordar un poco sobre los operadores lineales. Diremos que un operador es una función que va de un espacio Banach a otro espacio Banach que cumple la linealidad y la homogeneidad. Diremos que un operador es continuo o acotado si podemos garantizar la existencia de un real positivo M, de tal manera que cumple dicha relación con sus normas respectivas de cada espacio. Y pues también tener en cuenta que el supremo de este cociente pues se define como la norma uniforme del operador T, que es muy importante también tenerlo en cuenta para caracterizar la compacidad del operador más adelante. Listo, entonces ya una vez definido nuestro espacio, pues vamos a caracterizar la continuidad y compacidad del operador de composición con peso actuando en estos espacios de Lorentz, pero en primer lugar se define el operador, el cual es objeto de este estudio. Entonces, para una sucesión real U y una función Barphy en los naturales, el operador W sub U Barphy es aquella transformación lineal que aplica una sucesión X en la sucesión, en esta sucesión, ¿sí? Entonces, pues el operador se obtiene a partir del operador de multiplicación y el operador de multiplicación. Tenemos esos dos objetos, se aplica el operador de composición y luego el operador de multiplicación, que es prácticamente multiplicar componente a componente. Entonces, antes de caracterizar la continuidad de este operador, requerimos de esta definición. Diremos que una sucesión y una función Barphy en los naturales van a estar finitamente relacionados si podemos garantizar la existencia de un M tal que el número de las preimágenes de los unitarios va a ser menor o igual a ese M positivo. Para todo N que pertenece a este conjunto N, que se define como el conjunto de imagen de los naturales intersectado todos los N tales que esta sucesión es distinta de cero. Pues como ejemplo de esta definición, consideremos la función U de N igual a 0 si N es par y N si es impar. Y la función Barphy como igual a 2N menos 1. Entonces, este conjunto N pues sería el conjunto de todos los impares. Y luego pues decimos que bueno, la misma biyectividad de la función Barphy pues hace que el número de las preimágenes de los unitarios N con respecto a Barphy es igual a 1 para todo N en ese conjunto S, y por lo tanto pues U y Barphy van a estar finitamente relacionados por M igual a 1. Van a estar finitamente relacionados con M igual a 1. Entonces, para P y Q fijos con estas condiciones, vamos a decir que este operador de composición con pesos va a ser continuo si suponemos que U y Barphy están finitamente relacionados y además la sucesión U va a estar acotada para todo N en ese conjunto S. Entonces, como un bosquejo de la demostración, tenemos que si asumimos que el operador es acotado y la sucesión y dado que la sucesión canónica pertenece a este espacio, pues simplemente se verifica que la cuasinorma del operador evaluada en esa sucesión canónica pues es el valor absoluto de U sub N, y como el operador es acotado y la cuasinorma de la sucesión canónica es igual a 1, esto implica que la sucesión canónica, que la sucesión U sub N va a estar siempre acotada. Recíprocamente, pues, si la sucesión U y la función Barphy están finitamente relacionados y además la sucesión U está acotada para todo natural en S, entonces pues podemos garantizar la existencia de un K tal que la sucesión U y la función Barphy están finitamente relacionados y U va a estar acotada por ese mismo K para todo natural en el conjunto S. Luego, a partir de esto, y por propiedades del espacio, como la solidez de ese mismo espacio, pues podemos construir para toda sucesión en el espacio esta relación entre el reordenamiento decreciente y el operador W. Bueno, y dado que este espacio, bueno, como lo mencioné, es sólido, se puede verificar que es continuo, o sea, se sigue preservando dicha propiedad. Bueno, si queremos construir un operador continuo, pues simplemente consideremos el operador de composición con peso y una sucesión acotada. En nuestro caso, pues podemos considerar la sucesión 1 sobre n más 1, ¿sí? Y la función Barphy definida como Cn para todos los naturales. Es fácil ver que esta sucesión pues, está acotada y además Barphy y U van a estar finitamente relacionados por m igual a 1. Y pues, como cumple las hipótesis establecidas del teorema anterior, pues este operador con respecto a esta sucesión y Barphy pues va a ser acotado en el espacio de Lorentz. Y simplemente, pues si no queremos un operador continuo, pues consideremos una sucesión no acotada. En nuestro caso es U de n y si consideramos también la función que definimos anteriormente, se puede verificar que ambas son finitamente relacionadas, pero como le digo, no es continuado que uno es acotado. O sea, que este operador no es continuo porque uno es acotado. Bueno, otros resultados. Tenemos que, como consecuencia inmediata del resultado anterior, pues si se tiene que la función Barphy es biyectiva, en particular, pues si Barphy es la función de identidad, entonces el operador W en este espacio coincide con el operador de multiplicación. Decimos que al considerar la función Barphy biyectiva, la inyectividad de esta misma hace que la sucesión U y Barphy estén infinitamente relacionados para cualquier m positivo, para algún m positivo. Y pues si consideramos ahora la sucesión constante igual a 1, pues este operador coincide con el operador de composición, ¿sí? Entonces decimos que el conjunto S pues va a estar determinado por el conjunto imagen de los naturales y en particular se tiene que el número de las preimágenes de los unitarios n con respecto a Barphy va a ser menor o igual a n, a algún m, para todo n en ese conjunto S, y esto implica que U y Barphy van a estar finitamente relacionados para algún m mayor o igual a 1. Ahora pues vamos a caracterizar la compacidad del operador de composición con pesos en estos espacios de Lorentz. Pero primero recordemos que un operador lineal T, cuyos espacios de llegada y salida son de Banach, se dice que es compacto si la clausura de la imagen de cualquier subconjunto acotado en el espacio de salida es compacta en el espacio de llegada. O usualmente se dice que la imagen de cualquier subconjunto acotado es relativamente compacta. Bueno, como propiedades de estos espacios de estos operadores compactos, pues tenemos que si T es un operador compacto, esto implica que es continuo. La inversa no siempre cumple. Diremos que si la dimensión de la imagen del conjunto de salida es finito, entonces el operador es compacto. Diremos que una transformación que cumpla con esa condición, pues se llama un operador de rango finito. Luego todo operador de rango finito es compacto. Si T es una sucesión de operadores y T es un operador, si T es una sucesión de operadores y T es un operador que satisface que el límite de la norma uniforme de T sub n menos T es igual a 0 cuando n tiende a infinito, entonces esto implica que T es compacto, es decir, que el límite uniforme de operadores compactos es compacto. Y por último, pues tenemos una propiedad que nos dice que si T es compacto, si solo si transforma toda sucesión acotada en una sucesión que contiene una subsucesión convergente. Bueno, aquí sí es importante hacer un paréntesis y preguntarnos si toda esta teoría de los operadores compactos funciona también en operadores definidos en espacios cuasi completos. Y pues la respuesta es sí, dado que si el espacio de Lorentz es cuasi completo, entonces podemos garantizar que este va a ser equivalente a una métrica P y pues por lo tanto va a heredar propiedades de espacios métricos. Entonces, digamos, la primera propiedad se basa en el hecho de que un espacio métrico es compacto si toda sucesión contiene una subsucesión convergente. Entonces, es la idea de la propiedad. Digamos, la segunda propiedad sí es un poco más tediosa en el simple hecho de que este se basa en un resultado de Bolzano-Weierstrass. Y es que este resultado se basa en el tema de que en un espacio normado de dimensión finita, cualquier subconjunto de ese espacio va a ser compacto si es cerrado y es acotado. Entonces, esto es consecuencia de Bolzano-Weierstrass. Entonces, parte de la investigación que hicimos con el profe Julio era determinar que cualquier espacio de dimensión finita, estas cuasinormas van a ser equivalentes a la norma 1. Entonces, ya teniendo este gran resultado, pues podemos garantizar que este de la dimensión finita o el del operador de rango finito siempre se va a cumplir también para espacios finitos con las cuasinormas. Y bueno, entonces estos dos resultados siguientes ya son como consecuencias de estos dos primeros resultados. Tenemos que se supone que la sucesión U no es acotada y que el operador es compacto, ¿sí? Y luego, dado que la sucesión no es acotada, pues podemos garantizar la existencia de un épsilon, de tal manera que esta desigualdad con respecto a las sucesiones canónicas con cada distinto L siempre se cumple. Esto significa que la sucesión M sub U de E sub K no contiene ninguna subsucesión convergente y pues por lo tanto esto implicaría que el operador no es compacto, por lo tanto esto es una contradicción. Recíprocamente, pues si la sucesión U converge a 0, pues entonces podemos, para cada épsilon existe un n sub 0 de tal manera que esto siempre se va a cumplir. Y pues, dado que a la sucesión U se le conoce primer elemento, segundo elemento y tercer elemento, pues se construye una sucesión truncada, U sub n, que simplemente corta la sucesión original en algún punto, pues pasándose en el límite superior n para el índice. Y pues observa que cada U sub n es acotado y pues por el clorario de la continuidad, este operador de multiplicación, se puede decir que cada operador de multiplicación con respecto a esta sucesión es acotado en el LPQ, es decir, es continuo. Todavía más, este operador definido a partir de esta sucesión truncada es de dimensión finita y por esta razón también resulta ser un operador compacto. Luego, pues, se observa que esta relación se satisface y esto verifica que el límite uniforme de operadores compactos es compacto. Bueno, si queremos construir un operador compacto, pues simplemente construyamos el operador de multiplicación M sub U en los espacios de Lorentz con la sucesión 1 sobre n. Y ahora, si no queremos uno compacto, pues simplemente consideremos la sucesión armónica. Este es un claro ejemplo de que no todo operador continuo implica que es un operador compacto. Sí, porque esta sucesión es acotada, implica que el operador con respecto a esta sucesión es continuo, pero no es convergente, o sea, no converge a 0, entonces implica que no es compacto. Ahí está el ejemplo. Entonces, ahora vamos a caracterizar la compacidad del operador de composición en estos espacios de Lorentz. Listo. Entonces, tenemos a Barphy en los naturales, una función, y entonces el operador de composición es compacto en este espacio si el número de las preimágenes de los unitarios n con respecto a Barphy converge a 0. Estas funciones para las cuales cumple esta condición, pues vienen siendo aquellas que son acotadas. ¿Listo? Entonces, la demostración directa, pues, consiste en suponer que el operador de Barphy es compacto y que la sucesión B sub n no converge a 0. A partir de esto, pues podemos construir una subsucesión de valores mayores a 0, y a partir de esta sucesión, pues se construye otra sucesión en términos de los índices de la subsucesión anterior definida por este cociente. Además, podemos ver que esta sucesión es acotada en este espacio de Lorentz. Posteriormente, pues para n distinto de m se puede verificar que esta relación siempre se cumple, por lo que esto significa que la sucesión C sub Barphy de E sub n no contiene ninguna subsucesión convergente. Por lo tanto, este operador no es compacto y esto se dice que es una contradicción, dado que se supuso al inicio que este operador era compacto. Recíprocamente, pues supongamos que B sub n converge a 0, y a partir de que el operador C sub Barphy, se construye un operador truncado, y pues se puede verificar que la norma de la diferencia del operador C sub Barphy y el operador truncado es menor que esta relación. Y esto implica que el límite uniforme de operadores compactos es compacto, es decir, que C sub Barphy es un operador compacto. Como de nuevo un ejemplo, pues tenemos que, si queremos construir un operador compacto, pues podemos decir que el operador de composición con respecto a la función armónica es compacto, y lo mismo, pues, si no queremos nada compacto, pues consideramos una función que no sea acotada simplemente, y pues este operador con respecto a esta función no va a ser compacto. Bueno, ok. Bueno, antes de dar las conclusiones, pues podemos decir que hay un problema abierto, ¿sí? Y es que ¿cómo podemos caracterizar la continuidad y compacidad de este operador de composición para estos espacios donde P sub 1 es distinto de P sub 2 y Q sub 1 es distinto de Q sub 2? Aún más, pues quizás se pueda generalizar más estos espacios de Lorentz con otras características, no sé, ya sea pesos distintos o no sé, alguna otra propiedad que se implemente allí. Pero sí, este es un problema abierto, pues sí, quizás les guste. Y bueno, entonces, para las conclusiones para este estudio, pues se requirió estudiar, bueno, bastante de teoría de la medida, un poco de topología, bueno, análisis funcional, claramente. Y pues para esto se requirió también entender conceptos como el reordenamiento decreciente, la función de distribución, pues para luego definir el espacio de Lorentz. La continuidad del operador de composición en estos espacios de Lorentz se cumple siempre y cuando la sucesión y la función que la componen pues estén infinitamente relacionadas, y además dicha sucesión tiene que ser acotada. La compacidad del operador de multiplicación es equivalente al símbolo U que la define, converge a 0. La compacidad del operador de composición actuando en este espacio de Lorentz, pues se reduce al símbolo Barphy que la define, esté acotado. Y bueno, entonces quizás se pregunten que, pero ¿para qué sirven estos operadores en la matemática aplicada o en o en general, ¿sí? En las distintas áreas, pues los operadores en este espacio de Lorentz pues permite una mayor flexibilidad al tratar con funciones que tienen singularidades o comportamientos asintóticos particulares. Estos operadores también proporcionan herramientas y métodos para abordar nuevos problemas en matemáticas aplicadas y análisis teórico, especialmente aquellos que involucran funciones o comportamientos asintóticos. Y eso es, bueno, acá algunas de las referencias importantes que tomamos. Y gracias por su atención. ¿Alguna pregunta?
Ok. Miguel, muchísimas gracias por tu presentación, por tu muy clara presentación. Fue excelente.
Gracias.
Okay, so now we are open for questions. If someone wants to make a question in English, I can translate to Spanish the question for Miguel. Does anyone have questions for Miguel? Ok, creo que bueno, tengo una pregunta, Miguel, respecto a... No, está muy increíble este tópico de investigación, es muy chévere, digamos, los espacios de Lorentz son muy valiosos en análisis armónico, ¿no? En
Sí.
análisis de Fourier.
Okay,
Está increíble. Mi pregunta es si, digamos, esta es una versión de espacios de Lorentz, digamos, discretos para sucesiones, pero mi pregunta es si has considerado o qué tanto se conoce del problema que estás planteando, del problema que estás resolviendo en el caso continuo, en el caso en el que tomas...
Sí. No, sí, sí existe. Sí existe. De hecho, esto es un resultado de dicho problema que viene de los espacios LP, de funciones continuas. Ajá.
Ok, muy bien. Muy bien. Bueno, eso en primer lugar. Y otro, quería preguntarte, al final mencionas problemas abiertos, creo que es respecto a esta diapositiva, ¿cierto?
Sí, sí, sí. Ajá.
Sí, ¿podrías explicarme, digamos, de una forma un poco detallada en qué consiste el problema abierto?
Pues el problema es establecer la continuidad y compacidad de dicho operador. No está
operador.
Ajá.
Muy bien. ¿Y cómo es la definición de este operador WU-UFI? ¿Podrías mostrarme otra vez la definición de este operador?
Sí. No haberme pasado. No.
Algo que me llamó, algo que me llamó mucho la atención es que tienes condiciones necesarias y suficientes para la compacidad, ¿no?
Sí, correcto.
Es muy interesante. Entonces toma una sucesión y hace como, o sea, actúa como composición, un reordenamiento.
Sí, digamos, en un trabajo que hicimos con el mismo profesor, pues generalizamos estos espacios de Lorentz. Y además generalizamos también el operador, que se llama un operador bidiagonal, que, o sea, es más grande que este operador incluso.
Muy bien, o sea, la función U es una sucesión que tú escoges y así es que depende, ¿no? De U y de Phi. Y Phi es tu peso, ¿verdad? Tu peso.
No. El peso en nuestro caso sería U. Ajá.
El peso sería U.
Sí, el peso sería
Phi, ok. Y Phi es una función, una sucesión con valores, en los naturales. Claro, para poder que esté bien definida la composición luego.
Sí, señor.
Claro, y entonces tu pregunta abierta era ¿entre qué par de espacios de Lorentz será continuo este operador, ¿cierto?
Sí, pero ahora con P y Q, con P, o sea, con este P, ahora cambiamos la otra condición a P, o sea, con P distintos porque es que este va del mismo espacio al mismo espacio. Ahora, ¿qué pasa si yo le cambio las condiciones a ambos espacios? Que ahora eso es lo que toca analizar.
Claro, cuando cambias...
Cuando
cambias hasta... Muy interesante.
Cambiándole el peso. ¿Qué
cambiando el peso.
se requieren?
cambiando el peso. Es que está muy interesante el tópico. ¿Podrías mostrarme de nuevo el teorema de compacidad que tienes, la condición necesaria y suficiente?
Sí, bueno, me faltó justificar que la di por aparte porque faltó referencia sobre este tema, pero se está abordando ya en este momento ese problema. En este operador en particular, del mismo espacio al mismo espacio de llegada.
Una condición necesaria para que sea compacto es que la sucesión UDN vaya a cero.
Pero esto es de multiplicación, ¿no? ¿O qué es el de?
Este es de multiplicación.
Uh-huh.
Y para este operador, disculpa que esté haciendo preguntas, ¿no? Que está muy interesante. Y para el operador W, U sub phi, ¿tienes también una condición de compacidad?
Estamos abordando ese problema.
Ok, o sea, me imagino entonces que debe haber como un tipo de conjetura, o sea, como que U también debe ir a cero o algo como eso, ¿no?
Sí. Ajá. Sí. Se relacionan estos dos mismos conceptos de capacidad del operador de multiplicación y el operador de composición, pero sí. Por ahí va el asunto.
Está muy chévere. Sí, pues bueno, me gustaría mucho más conocer de este trabajo. Si quieres, envíame las diapositivas y pues si quieres pensamos algún tipo de problema relacionado con este operador. Está chévere.
Sí. O no necesariamente se podría hacer otro, no sé. Pero igual.
Algo relacionado.
Algo muy relacionado, exacto. Ajá.
Algo relacionado. Miguel, muchas gracias.
Vale, Eduardo, gracias a ustedes.
Okay, so it's very nice to see how much active is the young community of mathematicians in Colombia, a community that is doing the research in mathematics, in mathematical analysis, even from the very beginning part of their careers. So now we have maybe time to take a break. Today we didn't have break like in the other days of the conference. So maybe it's good to have a break and see all of you at 19 and 7 p.m. in Central European time and in 1 p.m. in Colombian time. So thank you very much.
Okay, thank you very much. So thank you to all the participants that are following our conference. It's with great pleasure that today I introduce Professor Anahit Galstian from the University of Texas in the USA, who will talk about the solutions of semilinear Dirac equation in the curved space-time. So, Professor Galstian, thank you very much for accepting our invitation. The floor is yours.
Okay. First of all, I would like to thanks organizers for giving me such opportunity to participate in this conference, especially devoted to celebration of the mathematical achievement of Professor Rodina. I congratulate him in his achievements. I met him several times during the conferences, and I wish him good health and further achievements in the mathematics. So today I will talk about the solutions of semi-linear Dirac equation in curved space-time. This is a joint work. Oh, just some technical. Okay, this is the joint work with Professor Karen Yagjian from University of Texas. And just a short abstract of my talk. In this talk, I will study solutions of semi-linear Dirac equation in curved space-time of the Friedman, Lamatre, Robertson, Volcker models of cosmology. We describe the relation between mass, scale factor, nonlinear term, and initial function, which will provide a global in-time existence or an estimate of the solution of the Dirac equation in the expanding universe. So that is like short introduction. Now let us recall that Dirac derived his equation in 1928 as follows. Here, this is the equation that Dirac derived. In H is a Planck's constant, alpha is a triplet of 4x4 matrices, and beta is also 4x4 matrix. Also, m is a mass, and c is a speed of light. And psi is a vector-valued function which belongs to C4. So it has, and this is a Dirac equation in Minkowski space-time. So that is a flat space-time. So my talk will concern about Dirac equation in the curved space-time. That was very important, like that problem to consider Dirac equation in the curved space-time was get actual with the construction of curved quantum field theory in curved space-time. And the standard model of cosmology provides such background. The model that we are going to consider today will be the Friedman, Lamatre, Robertson, Volcker model, which I will introduce in just a couple of minutes. For this space-time with accelerated expansion, that means more precisely the name of that space is de Sitter space-time. In 2020, Yagjian derived constructed fundamental solution of Dirac operator. And also in the same paper, he provided explicit formula for the solution of the Cauchy problem. Then in 2021, he examined the solutions. Yagjian examined the solution which given by these explicit formulas and asked to answer to such an interesting question in physics of fundamental particle as a validity of Huygens principle. Then several exact solutions of the Dirac equation in Friedman, Lamatre, Robertson, Volcker space-time, which is the basis of standard cosmological model, was obtained by separation of variable approach that they answer to some very interesting questions of physics. So one can look at the papers of Finster, Reintjes, De Oliveira, Schmidt, Zika, and many others. The behavior of particles obeying the Dirac covariant Dirac equation in this curved space-time has given rise to many investigations. So here some authors I mentioned: Schrödinger, Baruch-Duru, De Oliveira, Schmidt, Folk, Parker, Thoms, Zeka. On the other hand, the solution of the semi-linear Dirac equation describing self-interactive Dirac field in general, Friedman, Lamatre, Robertson, Volcker space-time, according to our best knowledge, haven't been discussed in the literature. My talk will refer to semi-linear Dirac equation. So what we do, we study semi-linear equation in the curved space-time, and then we focus on the connection and relation between several factors, such as mass term, scale factor, nonlinear term, initial function, which will provide global in-time existence or an estimate of lifespan or some conditions for non-existence or blow-up. So that was the main goal of our paper. In the large-scale dynamics of the universe, we ignore any small-scale deviation from uniformity and assume that on average the universe is isotropic and homogeneous. The mass in the universe can be treated as a fluid or gas with a constant density too. The galaxies or cluster of galaxies may be regarded as the particles or out of which this fluid or gas is made. The general homogeneous isotropic models of the universe with mass density, pressure, exactly what we are going to consider. This is exactly chain I mentioned, Friedman, Lamatrel, Robertson, Volcker model. Now, let us introduce the metric in that space. So the metric in this FLRW space is given in this form. So T is a time variable, X, Y, Z presents special variables, and AT is a scale factor. So the scale factor is determined by Einstein field equations for gravity. So that has to satisfy such that the metric GMW provided by this metric, yes, so this metric tensor GMW should solve determined from Einstein field equation for gravity. So the metric tensor in this case, in this Friedman-Lamatrel-Robertson-Volcker space-time, is given by the following matrix here. So here you can see the scale factor. We are going to consider the case when AT is a power function with A0 some constant function and TL where L is any real number. So we assume that X is from R3 and X0 we will assume it's just a T variable. So depending on this exponent L, for L less than 0, the space-time is contracting. When L is greater than 1, we have an expansion or accelerate. Expansion is accelerating. And L between 0 and 1, the expansion is decelerating. So depending on L, we have several models. For example, if L equals 1, it's newness space. And if we have this metric, in the case of AT has a degree 2/3, we have a model matter-dominated universe or Einstein-de Sitter model of the universe. If degree of T is 1/2, this model is about radiation-dominated universe. So this was introduction, and now we are going to consider the problem. First of all, we note that if we have the scale factor as A0TL, then the space curvature or Ricci curvature is given by the following formula. So here L is exponent of the scale factor, and then T is just a variable T, yes. And the Dirac equation in the space-time with the metric tensor that was introduced is given by as follows. So here is the Dirac equation in this curved space-time in Friedman-Lamatrel-Robertson-Volcker universe. With the A0 equals AT equal this. So what we can see here, so AT is the scale factor that was from the metric. Then gamma 0, gamma 1, gamma 2, gamma 3 are the contravariant matrices that have a such form. So here I2 presents identity, two-dimensional identity matrix, and O2 zero matrix, two-dimensional. So here we can see sigma k, and sigma k actually the Pauli matrices that are given as follows. So it's a 2x2 matrices. And also we have a gamma 5 here. It does not, we will use in the future, so which is product of those two. In addition, we see the mass here as contains mass in the equation and identity matrix. Now we are going to consider the Dirac equation with potential. So here, the difference between previous slide and this one, we have a potential here, and then we have a linear equation. So the potential, this V function, which is a matrix valued potential, assumed to satisfy, so to map this to M4. And one can rewrite this equation that with potential as follows, where alpha j, so the only difference, we just remove this gamma 0 somehow with notations, and we introduce alpha j, and we can rewrite the same equation in this form. So this, now we have this type of equation. Here you can see again, this is scale factor m and so on. Everything is there, but just different notations. We are going to impose nonlinearity, and here I'm introducing the condition on nonlinear function because we are going to consider semi-linear Dirac equation. Here is the definition. We will say that function f, which belongs to this space, is Lipschitz continuous with some exponent alpha in Sobolev space, HSR3. That means the norm of this difference satisfies the following condition. So if psi1, f psi satisfies the Lipschitz continuous with exponent alpha, we say if the f function is Lipschitz continuous with exponent alpha if this condition satisfies. So f psi 1 minus f psi 2 less than this, and this is the alpha. So the polynomial in psi vector valued function and functions like this. So these are the examples of such functions that satisfy to this condition. Here we have a gamma 0, a gamma 5, the matrices that we introduced before. And here you can also see the usual nonlinearities that we can usually consider when we consider nonlinear problems. So here are the examples of such functions. We are going to consider the Cauchy problem with initial time t equal 1. Also, we are going to assume that mass of the field or particle can be changing in time and vanishing at infinity. So, we are going to consider the model that determined with this, the model Dirac operator. So, this is Dirac operator, which is actually false. So, it's exactly the one we have before. And we can assume that M is complex number, so mass can be complex. So this model particularly includes equation of neutrino when mass equals 0, and as well as spin 1/2 particle undergoing to redshifting of its wavelength as the universe expands. So to introduce our first result, we need to introduce the space where we are going to solve the problem. And so we define the space X, R, K, L, M. So L and M are actually like mass, and then L is just the exponent that comes from scale function. So it's a set of all psi from this space such that the norm is defined as follows and bounded by some constant R. So here you can see the weight on, so for t from 1 to infinity. And, oh, what happened? Yeah, sorry. We assume that potential V belongs to BLK space, which is defined as follows. So BLK is a set of all V functions such that the derivatives belong to L infinity for this. So here alpha is multi-index, yeah, so it's a little bit. And L is also just, okay. The first result that I'm going to introduce, this is about small data global existence. So for simplicity, we are going to set constant in scale factor, which is I0, just the 1. And also, I remind that alpha j is just the product of this matrix. So first theorem. So let this psi phi of function, phi of c, non-linear function, so here, be the Lipschitz continuous with exponent alpha in HSR3 space with s greater than 3. And we assume that potential V is self-adjoint. In that case, the problem for Dirac equation, so here you can see this nonlinear problem, Fc is nonlinearity, with initial data at t equal 1, with condition that 3L greater than 2 times imaginary part of M. L is the exponent here of TL, and nonlinear factor alpha satisfying this condition, so 2 times 3L minus imaginary part absolute value of M for sufficiently small epsilon, and psi 0 belonging to H, so such that this norm is small. You see, we assume that norm is small. Then for that case, we prove that the solution to this Cauchy problem for semi-linear Dirac equation has a global solution in the space that we introduced, 2 epsilon S L M. So once again, I'd like to invite your attention to the condition for non-linearity, so for admission of this alpha, so for which alpha we do have global existence for small data. So here is the condition L, which contains this alpha, and in the theorem we have a following condition that alpha has to be greater than this function. So if the mass is real varied, then this condition becomes just alpha greater than 2 over 3L. And that means alpha should be greater than 1 when L equals 2/3. And alpha has to be greater than 4, and alpha has to be greater than 4/3 if L equals 1/2. Let me remind you that L equals 2/3 corresponds to Einstein de Sitter space-time, which is matter-dominated universe, and L equals 1/2 refers to the radiation-dominated universe. So for these two cases, here you can see again the same numbers, but I like to mention that for M equals 0 and L equals 2/3, for Klein-Gordon equation, in the paper of 2020, we've obtained the semi-linear term should be positive, and if we have alpha less than 2, then blow up appear. So here for alpha equal 1, for Dirac equation, we have alpha greater than 1, we have a global existence, but for alpha less than 2, for Klein-Gordon equation, we have a blow up. Of course, different equations, but really interesting connection. And also the similar thing true for L equal 1/2, in that alpha has to be less than equal for 4/3 for Klein-Gordon equation. So there will be blow up, and here for alpha greater than 4/3, we do have global existence for small data. So and for general blow ups, for Klein-Gordon case, the blow up appear for this cases. So, and now how we prove this theorem, I will provide slides like little details, but probably I won't introduce whole proof, of course, and we mainly prove this theorem by energy estimate and fixed point argument. So this metric tensor allows us to develop following energy estimate, which is the main tool to prove global existence for small amplitude solution. So first we obtain the energy estimate for this equation. So this is a Dirac equation, of course, linear one. And the energy estimate for the solution of this equation given us by following two inequalities. So here you can see that we have this exponent that was in metric, we have a mass, and then the right hand side. And so for t between s is greater than 1 and t greater for this parameter. Then we denote by s the propagator, which is the fundamental solution for the Cauchy problem. That is an operator valued function which solves the following problem. So here you can see the Dirac operator and also this initial condition, which is standard for propagators. So we are going to use Duhamel principle, and we can write solution. If we have an operator S, which is fundamental solution, then we can use Duhamel principle and write a formula for solution of this Cauchy problem with initial data psi 0 and right hand side fst. So then we are going to introduce operator S, which acts as follows. So application of S function psi is given by this formula. So where S in our case will be the nonlinear right-hand side of our semilinear equation. So using energy estimate that I introduced, we prove that this operator S is exactly contraction and for sufficiently small r, and so we also prove that S maps space X into itself for psi 0 for this space and for psi 0 initial data small less than epsilon, and moreover we have such estimates for this. And then we use Banach-Fix theorem to prove the theorem once and show there is a global solution for small data for that Cauchy problem. So that was the result for small data global existence. The next, we consider the equation again. We note that we have to say that this system of equations is symmetric hyperbolic system, and the local existence of the solution is known. That means the local Cauchy problem for this equation is well posed in some space for some t greater than 1. And the next theorem that we are going to state will show that some local solutions of the large data can be continued to the global one. So we consider the case when M is a real, this case, and V is potential function, which is self-joint. In addition, we assume that V potential function satisfies this equation. So here gamma is the matrix that we introduced before. And also we assume that our scale factor has a L greater than 1/3. And function f, nonlinear function, satisfies the given as follows. So this function is equal to some function alpha of this type and I beta. Here all these gamma 0, gamma 5 matrices were introduced earlier, and we assume that alpha and beta are real valued functions that satisfy this property. So alpha psi eta is O of this, and beta when psi plus eta approaches 0. And we assume that the psi 0 function, so initial function, satisfy the Lochak-Majorana condition, which is given as follows. So this function, which is written as this, so this again, gamma 0, gamma 5 are just matrices, and psi 0 is initial function, that this condition is Lochak-Majorana condition for any x from three-dimensional space. And also, here is the statement when we kappa 0, C0 is a function from C0 infinity. There is an epsilon 0 such that the Cauchy problem for Dirac operator plus Dirac equation plus this potential term, the potential term we already introduced the properties, and nonlinear function with initial condition given as psi 0x plus epsilon and this He function, which is this function, with epsilon between epsilon 0, epsilon greater than 0 and less than epsilon 0 has unique solution psi such that this solution belongs to C infinity case for all t from 0 infinity. So this is the theorem for the large amplitude, shows that there is a large amplitude global solution for this semilinear problem. Moreover, the solution, we prove that the solution scatters to free solution as t approaches infinity. I will just explain what actually we understand under free solution and what does it mean. So this remark, the last statement, means the following, that for every solution psi of this nonlinear problem, there exists psi tilde of the free Dirac equation, solution of the free Dirac equation, which is the solution of homogeneous Dirac equation, such that the difference in these norms actually approaches 0. So limit when t approaches infinity, this solution will approach free solution of free Dirac equation. So solution of nonlinear problem approaches the solution of free Dirac equation. So that means this was this statement above. We may talk about this later again, but I just like to mention here what we understand under the free solution. The proof of this theorem includes the following. We use successive approximations which were developed by Bachelot. He was using this approach to obtain estimates that obtain for nonlinear massless Dirac equation in Minkowski space-time. So the Bachelet introduced this, used this estimate, like obtaining some estimate for Minkowski spacetimes. So we follow his approach and develop some estimate for our case in the curved spacetimes. So also we replace generators of Poincare group with the Fermi operators, and then obtained energy estimates allow us to expand the results obtained by Bachelet to Dirac equation in Friedmann-Lamattre-Robertson-Volter spacetime. So to obtain our results, we prove several lemmas. I just will shortly introduce the slide. So first we prove lemma that for matrix-valued potential A of this form, where the alpha and beta were introduced before, the solution of Dirac equation, of such Dirac equation with A psi on this side, satisfy the following identity. So the norm of solution can be written as follows. That was first lemma. Then there is the second lemma is about potential. So our condition in our theorem, we have a condition that potential should satisfy this inequality, this equation. Then for the solution, the lemma claims that for the solution psi of our problem, so Cauchy problem, the following identity held. And here you can see the integrals, and then psi is the solution. Here you have xt, and here is initial at t equal 1. In particular, for z complex, with module z equal 1, we have the following equality. So that was lemma 2, so that describes the behavior with this potential satisfying this condition. Again, this is about, this condition is in our theorem. Then we prove this estimate, this equality for the solution. So that was the lemma 3. And then we prove also the following corollary, that if we have a potential that satisfies condition of the theorem, and if imaginary part of mass is 0, then this equality held, and if imaginary mass is not 0, then for the solution of Dirac equation, that this inequality holds here, the equality holds here. And the third one is such that, I mean, these are all technical estimates. So then we have the inequality. So if we have the difference between these functions 0, then we can have such inequality. So the last statement of the corollary contains actually Lochak-Majorana condition of theorem 2, which is written in this form. Okay, and now we will I will address more the asymptotic affinity for the case. Will show that when the solution approaches Dirac equation. So for the nonlinear function, which is Lipschitz continuous with some exponent alpha, such that this alpha 3L alpha L greater than 2, then for every solution psi of our problem, so if my f function is such that this condition satisfied, then we can find C tilde of solution of the Cauchy problem for free Dirac equation like this, such that the norm equals 0. That was exactly the statement that our solution approaches free solution when t approaches infinity. So, the next result that I am going to introduce will be about non-existence of global in-time solution. So let us consider energy integral, which is defined as usual in standard form, and we are going to consider the following Cauchy problem. So here we have a same zero equation in the curved space-time, and the right-hand side given as follows, where gamma 0 is just a matrix that was introduced, and this function g zeta satisfies the following condition, and also this condition about this nonlinear function here. And we assume psi 0 has a support in this set, some bounded set. Then the statement of theorem is follows. For arbitrary size initial data, there is no global solution psi of the problem 11 that obeys the finite propagation speed of property. So finite propagation speed property, we define as follows in this case. We assume that support of solution should be in the set given by this. So modulo of x has to be less than some r plus at, where at is the following integral. So here you can see this a tau, like this a function, is the scale function from the metric. So there is no arbitrary size. For arbitrary size initial data, there is no global solution for any initial data for the following cases. If L is greater than 0 or less than 1, and alpha such that satisfy the following conditions. So the 3 alpha over 2 plus alpha imaginary path mass has to be less than 1. Also, for L greater than 1 and this number less or equal 1, we also have no global in-time solution which obeys this propagation property, and therefore L equal 1, the same is true. Furthermore, in the following cases, there is no global solution for large initial data that obeys the finite propagation of speed of property. So here are the conditions for L such that this so the problem has no global solution for large initial data which obeys the finite propagation speed of property. Moreover, the solution blows up no later than TBU, so we give the estimate for the lifespan. Actually, here we say that is some number. We don't have an estimate for this, but we can predict that there will be some number TBU which depends on coefficient C0, alpha, so alpha that was the nonlinearity, mass, initial data, and exponent L of the metric such that this energy equal given by this integral. So here you can see the AT, that was the integral that contained the scale function, and that limit of this integral, which is energy of our solution, will approach infinity once t approaches that TBU, provided that the energy is initial energy is sufficiently large. So that was the last result that contained here. I like to remind you that I was considering this Cauchy problem. And for this Cauchy problem, for Dirac equation in curved space-time, semi-linear like this, like nonlinearity provided by this G function, we obtained non-existent for arbitrary size initial data, which also for large initial data, and also we have we proof that the solution blows up no later than time TBU. So energy is infinity, so provided that initial energy is sufficiently large. That was all. Thank you very much for your attention, and thank you very much once again for invitation.
Okay, Professor Galcian, thank you very much for your very clear talk. Now it's time of questions. Are there the questions for Professor Galcian? Remember that you can raise your hand if you want to make a question to Professor Galcian. Okay, Professor Rodino. Professor Rodino. Can you can you unmute yourself?
Okay. Beautiful seminar, Anaito. A question would be, at the beginning you told several physical interpretations about the universe enlarging or restricting. There is some physical meaning that you find in blow up. Blow up means that something is exploding. Of course, you need to have a global solution, it will be better, but I think you have shown that this is impossible under some conditions.
Yes. These models actually very depressing, I have to say, because they show actually that our universe is expanding. So in our case, we have a polynomial function here. And so usually then there is a de Sitter model which has an exponential factor, a scale factor, which is actually showing there is a proof that the universe is expanding with acceleration, and some blow up probably expected, of course I don't know. But in our case, we have three results. We have a small data, global existence, a large amplitude, global solution, but also we have the blow up for this model, for Dirac equation, for the special case with potential with a nonlinear term like this. Yes. So I don't know if I responded to your question.
Yes. Thank you very much.
Thank you very much for interesting question.
Thank you, Professor Rodino. Thank you. Are there more questions for Professor Galcian? Maybe I have a question, maybe a little bit technical, about the theorem 1, the result that you label theorem 1, right? Here I wanted to maybe to ask, just as a curiosity, from where came these conditions on your parameter alpha in the equation 6, that alpha is larger than twice and that quantity that appeared there. From there it does appear this.
You mean this? This comes from the proof, of course, when we obtain the estimate you see this proof was based on the energy estimate, which contained exactly this factor. And when we have to prove that this is a contraction, we will use the energy estimate, which contains this actually.
Okay. It's about the method, right?
It's a method and also space. We define the space. If you see, I have a definition of the space somehow. There is also this weight. Here, you can see it comes from the space also. Yes.
Okay. And okay, no, that's clear. That's clear. That,
okay, thank you very much.
Alpha, right, comes from there. Maybe another question is if this condition on alpha is sharp, but right, it's from the method that you explained. Right. Okay, thank you very much. It was very clear presentation.
Thank you for the patience.
Are there more questions for Professor Galstian? Okay, if not, then Professor Galstian, thank you very much for accepting our invitation.
Thank you very much too, and hopefully we will meet sometime in person.
Maybe, yes, that will be great. I invite you maybe to follow the other presentation, especially tomorrow.
Sure, I will. Okay. Thank you.
Maybe to follow our closing ceremony tomorrow.
Definitely. Thank you.
Thank you very much. Okay.
Should I close this?
Maybe you can stop sharing, right?
Yeah.
Thank you very much. Okay, to our participants, then we are going to resume in 10 minutes, exactly in 10 minutes, with our next talk. Julián, ¿estás allí? Okay, thank you very much to all the participants that are following our conference. It's with great pleasure. Please continue.
Thanks, Duban, for
Please continue.
thanks, Duban, for so nice presentation of my talk. Thanks you all for being here. And thanks for the invitation to share with all of you my work and a part of my work. We will be talking about new solvability conditions for boundary problems for polymonogenic and inframonogenic functions on fractal domains. Here, fractal domains, we are talking of domains with fractal boundaries. We'll start with presenting the Riemann boundary value problem in complex analysis. Professor Bori was talking a few days ago about this in the idea of open boundaries, but we are talking here with closed boundary, a closed curve. But we are going talking about generalization, the relation given for the formula in the presentation, and that nullified in the infinite. Here we have a representation of the curve, the disposition of the domain, the interior domain, the stereo domain. We are assuming, of course, that the curve is smooth and is a Jordan curve, allowing us to talk about interior and exterior domains. When we have the coefficient function g, capital G is exactly equal to 1, we have the Young problem. In the case of a smooth curve, we have that the solution of the Young problem is given by the Cauchy type integral, here in complex analysis and also in Clifford analysis. But when we are talking about curves that are row, even rower than, for example, Cauchy snowflake, that is a fractal curve, we don't have any sense of a complex integral because we don't have rectificability. And so we need to use another approach, another methods to try to solve the problem, because the problem is have complete sense. However, the standard method is what is not working here. Around 1983, Boris Katz gave a complete treatment of the problem in complex analysis, and he find a condition when we can solve the problem. The problem is solvable given this relation between the Holder exponent nu of the Holder function, the data functions, and the upper Minkowski dimension of the curve. The idea we are talking about in general about Clifford analysis, and we will take complex analysis like a special case of treatment, and we have that complex analysis provide a natural generalization of the complex analysis of higher dimensions. And here, in the context of Clifford analysis, a complete treatment of Riemann boundary problem is still an open problem, mainly because the not commutativity of the product in Clifford algebras. That is why the study of this kind of problem for domain with fractal boundaries is mainly focused in the Young problem and some special case. In this sense, the results about the involving the Minkowski dimension we just talked has been generalized to higher dimension for mainly Professor Ricardo Abreu and Professor Juan Bori. However, the main goal of this word, of this presentation, is to talk about solvability conditions involving a new metric characteristics of the curve surface in general of the boundary that is called Marcinkiewicz exponent. And with this, we want to try to prove that the solutions, the solvability conditions with this metric characteristics are better than the previous one. We need to talk about a little bit about Clifford algebras that are the natural extension of Rn to a unitary associative algebra that satisfies the product relation given in the slide, and from that we can derive the following construction when the product we need to define an algebra is given for the relation given there, where the Kronecker where the delta Ij is the Kronecker delta. And we can think about any Clifford number of a linear combination of the element of the base, where the base is a given product of the n element of the standard orthonormal base of Rn. And here we can define a conjugation as the anti-involution given there. Also, we have a norm, and we can talk about the space of K vector as the span of all the linear combination of all the E sub A with all the same amount of element of the orthonormal base in the product. We can see the Clifford algebra as even the direct sum of the even algebra plus an E1 the even algebra again. And we also have the relation. We can identify any element of the Rn plus 1 with a number, a Clifford number, and also we can identify any element of Rn with a Clifford number. We have in the first case the space of paravectors, and in the second case the space of vectors. And the functions that we are going to consider are functions taking value in the Clifford algebra, which are defined in Rn plus 1 or Rn. And we have a Cauchy-Riemann operator in Clifford analysis. And we also use a Dirac operator in Clifford analysis. And we talk about monogenicity as function that nullify this operator. In general, we have left monogenic functions, or right monogenic functions. It depends of the position of the operator with respect to the function O. We have the fundamental solution of this elliptic operators. And we will need to use for the proof of the result, Theodorescu transform that is an integral in the domain, an integral transforms in the domain. As we see probably in the case of the plane, and in general in the case of the Clifford analysis also, the problem for a smooth curve or a smooth surface, in general a smooth boundaries, the Cauchy type integral in complex and Clifford analysis is the solution of the Young problem, but the Cauchy type integral is a boundary integral. Here we need to use to change the approach, and we are going to use integral transforms in the domain. We will talking about polymonogenic functions as functions that nullify the Cauchy-Riemann operator k times, and we are going to talk inframonogenic function as function that nullify the Dirac operator from left and right simultaneously. We can talk, actually the definitions can be given using the Dirac operator k times and the Cauchy-Riemann operator from the left and the right. However, this is the context and the way in the most of the work has been developed until now, and we will be following these definitions. Now we need to talk a little bit about fractal dimensions. And in order to talk about the Hausdorff dimension, we need to talk about Hausdorff measure, and the Hausdorff measure is the limit when lambda tends to 0 of the number h as lambda. We can prove that this Hausdorff measure take almost always the values 0 or infinity, and it change the value in only in one point. When we can have this point, the value of the Hausdorff measure could be infinity, 0, or finite. So it makes sense to define the Hausdorff dimension exactly in this point. The upper Minkowski dimension will be defined as the superior limit given in the slide, where we have the logarithm of the number of smaller number of set of diameter atmos delta covering the set E, and we have a relation with these two dimensions, where we have that always the dimension Hausdorff dimension is less than or equal to that upper Minkowski dimension, and from that we can define a fractal in the sense of Mandelbrot when the Hausdorff dimension is strictly greater than the topological dimension of the set. We will require the definition of Holder functions, and here we will call it Lichtchen function with exponent nu for regularity in the exposition, and we will need to use the definition of Lipschitz functions with arbitrary exponent nu, or k mas nu in this case, where we need these functions to satisfy the relations 2 and 3. These class of functions are at the same time generalization and refinement of the classical Holder functions. We will require also the Whitney extension theorem that when we adapt it to our language of Cauchy-Riemann operator, give these results. And we require a suitable version of this problem for the Cauchy-Riemann operator for polymonogenic functions and inframonogenic functions. All of these versions can be easily shown that are adapted of our for the original the Whitney type extension theorem present in the book of Stein, Elian Stein. And for the proof of the kind of unicity in a class theorems, we will require the Dolchenko theorem, Dolchenko time theorem, that is a theorem that give off condition for the removability of the singularities and basically plays the role of Pine-Levi theorem, and who did this theorem together with Liouville theorem and Clifford analysis give the result for unicity in a class theorem we were going to see. Well, going deep on our results in our presentation, we are generalizing a concept of Marcinkiewicz exponent that was given for first time in the plane, and we are presenting for David Katz, and we are presenting this in the concept in higher dimensions. We have this integral that is depend of the distance of x to the boundary S, that is fractal in general, and we define the upper and inner boundary and satisfying the boundary, the equation 5. And we were able to prove this new solvability condition involving the Minkowski dimension, and the main idea of the proof of this theorem is to find suitable conditions for the Cauchy-Riemann operator over the extension of the function f, the extension of the function f, that f is the data of the problem. We need to this new function to be LP, and with these conditions we are able to use the very good properties of the Theodorescu transforms, and with that we are able to show that the function given for the equation 7 is actually a solution of this of the Young problem. We, as was recently talking about, we are able to prove a kind of unicity in a class condition. We have that is a function is in the class of Lipschitz function with exponent null, where null satisfy the conditions given in the equation A. We have that these functions are unique in this class, and of course is given for the functions we just present. So we have obtained a new condition. However, why it's worth to actually show that these results involving the Minkowski dimensions are better or equal to the conditions involving the Minkowski dimension as given for this theorem. However, we go further and actually can prove that there are boundaries for any dimension in any Clifford analysis we are talking in Rn. In Rn we are talking about there are always not countable collection of topological compact hypersurface that actually the metric characteristic in the Marcinkiewicz exponent is better, strictly better than the one with the using the Minkowski dimensions. And that is happening for any value between n and n+1. And the sketch of the proof, there is not any magic. We actually construct the surfaces, and the idea is to add suitable n-dimensional rectangles to a cube, and taking the boundary. We have in the two-dimensional case in the plane this is how we can see the curve in this case. It's worth to mention that this curve, this particular case of the plane, is pretty similar to one given for David Katz in an example years ago, and the main idea, the core idea, is going to the seminal work of the late Boris Katz in 1983. Well, continue with our generalization of this. We have a visualization of this kind of boundaries in the case of 3 dimensions. And the idea is that we can prove that the Marcinkiewicz exponent of this surface are always more than or equal to 1 minus beta minus n divide between alpha beta plus 1. And we can also exactly find, no bound, the Minkowski dimension of this surface for any value of n, and it's easy to show that for this curve we have for these boundaries in general we have the strict inequality, and we can for a suitable beta give that we are doing this for any value between n and n+1. But we still want to go further and actually give an example, a problem that is not solvable with the solvability conditions, the previous solvability condition, and is solvable indeed with these new solvability conditions. Well, it's not solvable with the previous condition, but we can say that it's solvable with the previous condition. We can say anything about the problem with the previous condition, but with the new condition involving Marcinkiewicz exponent, we can guarantee that this problem is solvable and give the solution actually. Well, we are using as boundary the surface given before, presented before, for a general alpha and beta, and the function f will be as follow when we are taking advantage of the a classical result of Lipschitz function and Holder function for real functions. So we are putting there this function, this real function in the expression of our general function f that is take values in the Clifford algebra for n equal to. We have our problem, and it can be shown. It can be shown that this problem this function is the Holder with any exponent less than beta divide between beta plus 1, but is not a Holder with any exponent greater than that. That means that we cannot say anything about the problem using the previous condition, but we can actually say that the problem is solvable using the conditions with the Minkowski dimension and actually give a solution that is given by the formula presented before. Well, we are now in condition to talk about polymonogenic. That is the next step we took in our work. In the case of polymonogenic, we want to find a polymonogenic function, and we want to the conditions on the boundary are k condition is in the boundary and k conditions are nullifying in the infinity, and the function f ball fe is a reference of the f aj in the expression of the Lipschitz function. We need to use, in this case again, a kind of polymonogenic Theodorescu transforms, where we are used the kernel of the polymonogenic function of the operator, the Cauchy-Riemann operator applies k time, and we have that in the case n equal 1, k equal 1, we have the classical kernel, and we have the derivative of this kernel give the previous step when we apply the Cauchy-Riemann operator. We are able to prove a new condition, again, in the case of polymonogenic function, that are similar in the expression only of the one for monogenic function. We are able to show that this problem is solvable for this condition, the condition 10. We also need another one condition in this case, where we are talking to k to be strictly less than n plus 1, but this is strictly for the nullify in the infinity. But if we do not include that condition, we also have solvability without this extra condition here in the polymonogenic function. And the proof is more or less similar. We need to use the condition for this Theodorescu transform polymonogenic, and we also can find a kind of unicity in a class theorem, again making use of the Dolchenko theorem and Liouville theorem. But in this case, we need to apply the previous unicity in a class theorem we find before k times, and we need to actually do it for induction in K. For the case of polymonogenic functions, we need again define a kind of Theodorescu transform from monogenic Theodorescu transform, when we are used these integrals in the expressions, and we use this kernel, the fundamental solutions of Dirac operator and Laplace operator respectively. And here we are now using the absolute Marcinkiewicz exponent we saw before, because we are not only trying to generalize the functions for generalized functions, we also want to continuously improve the geometric condition that we are dealing with. So we are going to present a little bit of refinement, and we call it refined Marcinkiewicz exponent. This presentation deal with more or less kind of integral, and we starting by defining the general exponent, Marcinkiewicz exponent, as as the supremum of this set with of the value of p where the integral is convergent, the supremum of values p, and we can show actually we can define actually the when the S is a boundary. We can talk about inner and outer general Marcinkiewicz exponent. These are kind of auxiliary definitions. Will be showing that are pretty similar to the ones previous before, and we can show, as we were talking before, that this the general inner and outer are exactly the same. That the inner and outer absolute Marcinkiewicz exponent, but in the case of a general Marcinkiewicz exponent, is not exactly the absolute Marcinkiewicz exponent, because in this case is the minimum and the absolute Marcinkiewicz is the maximum of these two values. And the idea this proof is practically taking neighborhoods and showing the similarities of the definitions in some case. And we can also define a local version of these definitions, taking a ball with center in T and radius R, and the intersection of this ball with S. So we are then defining the local Marcinkiewicz exponent as the maximum supremum p, where we have the convergence of the limit of the integral, and we have this local Marcinkiewicz exponent depending not only on the set A, but also of T, the center of where we are talking about the local regionality of the evaluation. We also have the definition of the inner and outer when S is a surface, in general a boundary. And using that, we can find a relation between the inner and outer Marcinkiewicz exponent and these local versions. So we can take the infimum over all the points of the boundary. And we can take the refined Marcinkiewicz exponent as the infimum of the maximums in any T. There is possible to show that there are this chain of inequalities, showing that in general this refined Marcinkiewicz exponent is better or equal to the absolute Marcinkiewicz exponent. That implies that the possible conditions we could find here will be better. However, again, we can find an example where this refined Marcinkiewicz exponent is better than the absolute Marcinkiewicz exponent. That would mean that for some functions or for some boundaries, the solvability conditions we will find will be better than the ones using even the Marcinkiewicz exponent that we used before, and therefore are better than any other possible conditions that are using that the Minkowski dimension. Well, we again construct in this case only in 3 dimensions. We have a cube, and we will be adding and deleting some 3-dimensional rectangles, and visualization of this idea will be like that, or that's that values of alpha and beta. Well, we can we have here a couple of points that are wild. These wild points are our focus in this case of are talking about involving the local Marcinkiewicz exponent that is in the definition of the refined Marcinkiewicz exponent. So in the local Marcinkiewicz exponent, we need to focus in points and neighborhood of these points, and we have two wild points. The point, the origin 0 and the E2, and we can show that in these points we have these values of the inner and outer Marcinkiewicz exponent, and this is interesting because well, in any other point we have trivially that it's straightforward to show that is 1 because in any other point, a sufficiently small neighborhood of any point, these are have Lebesgue measure 1 and Hausdorff measure 1, and are is sufficiently small near any other point that in any neighborhood that do not include the origin or E2. And then, from the definition of the inner and outer Marcinkiewicz exponent, we can show definition and the characterization that we show through the local Marcinkiewicz exponent. We can show that the inner and outer Marcinkiewicz exponent takes this value, but the absolute the refined Marcinkiewicz exponent takes this value because we have, in any case, we have in a point we have the one of the two values inner and outer local Marcinkiewicz exponent is this. So when we take the infimum, we have this value, and therefore we have that indeed for any alpha different to 1, we have the state inequality. So we are going to use this refined Marcinkiewicz exponent to show talk about the solvability conditions and for inframonogenic function. It's worth to mention that this problem, to the best of my knowledge, was only treated very fast in a previous paper, in a section of previous paper with again the authors use the Minkowski dimensions that we showed long before that this condition will improve that solution when we present it. And the idea is this, that we have the Young problem and Young problem for functions with the operator from the right. We can also analyze the problem with the operator from the left. It's an analogous problem, and the nullify in the infinite. Here, the function ball f01 is also a rearrangement of the components of the Lipschitz function with arbitrary exponent. And then we find an analogous condition with analogous only in a statement with using here the refined Marcinkiewicz exponent. And the idea here is a little bit more sophisticated, but is to construct this joint subcovering, because we are with a compact boundary. So the boundary is a compact surface, and adapting the problem to any of these small balls covering any valve of, or no valve, but almost valve, and then adapting the problem to these sections, and then trying to solve the problem in this any of these sections, and then we need to apply the suitable Winnick type extension theorem and the definition of this exponent, together with the properties that are very important, the properties of the Teodorescu transform. And in these conditions, we will have that the sum of all these sub-solutions will be a solution of the general problem. And again, we can find a unicity in a class theorem where we need to use auxiliary functions for the problem, as is quite straightforward once we have the previous one. And these results are mainly contained in this paper, and the last one is still submitted, and I still have not uploaded any preprint, but I will do it soon. Thanks you all for being here. I really appreciate your time, and thanks. Okay, I done.
Okay, Carlos, thank you very much for your very nice talk. At this moment, is a time for questions. Does anyone has questions for Carlos? Remember that you can raise your hand. You can raise your hand, and then we will allow you to unmute your microphone to make your question. Okay, maybe I have a question, Carlos. I don't remember well maybe the number of the slides, but was this slide where you define the integral E sub p, right?
Okay.
When you were defining the Marcinkiewicz exponent, I think that was the equation 4. Equation 4. I remember that was equation 4. Maybe you can share your presentation again. Maybe?
Yeah. Okay.
Your presentation.
Are you seeing my presentation?
I see your presentation.
Okay.
Yes.
Give me a second. Okay. Equation 4. Okay.
Equation 4.
Okay. Okay. This is not. This. No. Yes.
Maybe later.
Yeah. Too much. Okay.
4. Here. Yeah. So, okay, here you define this integral E sub p omega, right?
Yeah.
And okay, then it's clear the dependence of the parameter p, right? It's clear the dependence of the parameter p. My question is if do you know literature, right, where you consider instead of the constant exponent p, which is a Lebesgue exponent, something like a Lebesgue exponent, if you consider a function p of x, right? I mean, taking inspiration from these Lebesgue spaces with variable exponent, right? Remember that you have LP spaces, and when you define LP, okay, you have a number in the condition of the convergence, but also there is a version in which you consider the Lebesgue spaces with variable exponent, and then you have a function p of x satisfying some conditions, right? Some suitable conditions. My question is if it makes sense maybe to analyze this integral also considering the function p of x.
Actually, I think it could make sense. I explore another way. I use in place of consider a function in the exponent p. I consider a function in the whole denominator. For example, we are using here like a TP function, where the argument of the T supra P is the distance. So I am consider in the future, when the future work, not in work that I am currently doing, I am consider functions in the entire the denominator, but I think that and is actually giving me results with that, because the main idea for me is that we need to solve the problem, not only continuously improving. And I think the idea is giving something like that, and giving that is giving us a continuous improvement of the problem. Yeah.
Okay.
But I think that could be worth of considering that kind of generalization of this definition.
Okay. Thank you very much.
Thanks.
Thank you very much.
To you.
Professor Juan Boris Reyes, maybe can you unmute your microphone? Can you activate your microphone, Professor Boris? Maybe now you can activate your microphone. Professor Boris Reyes, can you hear me? Maybe you can activate your microphone. For some reason, we cannot hear you, Professor Juan Boris Reyes. And you are now co-host of our meeting. Maybe I think you have the permission to activate your microphone. Okay, sorry. Or maybe you can write your question. If maybe you have problems to activate your microphone in the chat. No, we cannot hear you. Sorry. Or maybe, okay.
Should I stop sharing or something?
Let's wait a little bit. If Professor Boris, Juan Boris, okay, maybe. It's a problem with his PC, but maybe you can write your question, then I can read it. In the meantime, maybe we can hear the question by Lianet de la Cruz. Lianet, can you activate your microphone?
Yeah. Could you hear me?
We can hear you well, yes. Please make your question. Thank you.
It's just a simple question about the Lipschitz class that you use in your results. Also, we are talking about higher order Lipschitz class. You also use this notation for Holder class in order to keep it has something to do with the notation. It's just a matter of notation. But I would like to know if you obtain those results in, for example, this boundary value problem for inframonogenic functions or for polymonogenic functions, just only for higher order Lipschitz class of order 1, that is 1 plus nu, or also for for every order k. I just make this question because I saw in your boundary value conditions, I just see involved the function f01. That means also that makes me think that you are only using the first order Lipschitz class and not the higher order Lipschitz class. That's only the question is only because of this.
Okay, so, I understand. I will share again. Yeah, mainly when can you see my presentation?
Just a moment. Yeah, no.
No?
Yeah.
Okay. Okay. Let's see. Okay. The problem. Minute. Okay. When we are talking about polymonogenic functions, we are using the Lipschitz functions k plus nu. Yeah, in general, of course. We are here with k plus no. Well, k minus 1 plus no. And but it's important to notice here, this is a special rearrangement. It's not exactly the functions in the components of the develop of the Lipschitz function in arbitrary exponent. Is a rearrangement in this. Can you see my mouse?
Yeah.
Okay. In this function, you have all the functions.
All the set.
Yeah, you have all the set that the absolute value of the multi-index in these functions are the same integer value.
Okay.
It's the if you have I equal 2, for example, you have the functions 0, 1, 1, 0, 0, 0, 1 and 1, 0, 0, 1. All the functions are in there. Is a rearrangement of this function. All of them are there with the absolute value of the multi-index are the same. I maybe should try to include
just a matter of
in the
notation.
presentation.
It's not the same I'm usually to use in my work.
If we go
kind of class.
Okay. Yeah. For example, all the ones that have the same k are in the is a rearrangement of that fi. Sorry, language. Fi. Yeah, are in the same rearrangement. Actually, in fi, bold fi, we have actually the units of Clifford, the basis of Clifford of the orthonormal basis of Clifford algebra. Actually, in that rearrangement,
the part where you define the bold f, and then that's why my question.
Yeah. I didn't include it, but and then when we are talking of inframonogenic, I am only in.
You only use
you made your question
you only
made
have
complete sense.
Practically two order operator, and then
exactly
you don't need more functions of this set. But okay. Yeah.
When we talk about inframonogenic function, a little bit, a moment. Okay. When we talk about inframonogenic function, I don't include the class of the function, data function here. Yeah, I do not include, but yeah, we are in a class of 1 plus no. Yeah, because our operator have is a k equal to something like that, no?
Yeah. Okay. Yeah. Thank you for your acceleration.
Thank you for your question. Okay. Always a pleasure. Here again is a rearrangement, the F01.
Yeah, now it's clear to me why so it should be interpreted as this collection of order one functions of this set. Okay. Thank you, Carlos.
Thank you. Yeah.
Okay, very good. Thank you for the question, Leonette. Okay, Carlos, thank you. I think maybe it's time to finish. It's time to finish our scientific program today. Just maybe because tomorrow is the last day of our conference. I want maybe just to share some practical information. Can you see my screen?
Yeah. More or less.
Okay. Okay, thank you. So tomorrow is our last day, right? We are going to start at 14 in Central European Time, 8 a.m. in Colombian time, with the talk of Professor Bernstein. But then I encourage, let's say, to attend tomorrow the closing ceremony, also the talk of Jacqueline Mesquita, who is actually the president of the Brazilian Mathematical Society. And also tomorrow we are going to have the Ekman presentation, which is not a presentation about mathematics, but it's a presentation planned to white audience that the speaker will be Jiraira Betishan, which is an Armenian mathematician, and he will talk about challenges of doing mathematical research in developing countries. So I really encourage to all the people, to all the attendees, maybe to join us tomorrow. And thank you very much for your participation today. So thank you to all the speakers, and see all of you tomorrow. Thank you very much. See you. Bye-bye. Listo, Julián. Podemos finalizar la presentación.
you.